Hello there and welcome to Physics with William, where curiosity gets comfortable, difficult ideas take their time, and science is allowed to speak in a quiet voice. Tonight we are looking at something that is almost everywhere in the universe, even though most of us rarely think about it. It appears in stars, lightning, glowing signs, laboratory machines, and the space between planets. It can be hotter than the surface of the sun, cold enough to touch under the right conditions, brighter than a city street, or nearly invisible. It behaves like a gas, but it is not simply a gas. It carries electric charge, responds strongly to magnetic fields, and often moves in patterns that seem almost alive. This strange state of matter is called plasma. The word may sound familiar for more than one reason. You may have heard it at a hospital, where blood plasma carries cells and nutrients around the body. You may have seen it on a television advert for a plasma screen. You may have heard it used in discussions about fusion energy, space weather, or experimental engines. The same word appears in several places, which can make the subject feel more confusing than it needs to be. The plasma we are discussing tonight is the physical state of matter. It is not blood, and it is not a mysterious liquid hidden inside electronics. It is a collection of particles with enough energy that ordinary atoms can no longer remain completely intact. That sounds dramatic, although atoms are not being destroyed in the way the word might suggest. Their central nuclei remain. What changes is the relationship between the nucleus and some of the electrons that normally surround it. In an ordinary gas, atoms and molecules travel freely and collide with one another. In plasma, at least some electrons have been separated from their atoms. The result is a mixture of negatively charged electrons, positively charged ions, and often some neutral particles as well. Because electric charge is now free to move through the material, plasma behaves in ways that an ordinary gas does not. Before we go any further, where are you listening from tonight, and what is the sky like outside your window? Is it dark and clear, with a few stars visible, or hidden behind clouds and city light? Perhaps you're somewhere warm, listening with a window open. Perhaps rain is tapping against the glass. Perhaps you are already in bed, wondering why a subject connected with lightning and stars has been chosen for a relaxing science journey. That is a fair question. Plasma can sound energetic, noisy, and rather difficult to keep in one place. Fortunately, we do not need to build a fusion reactor beside the bed. We can simply take our time and understand what plasma is, where it comes from, and why it matters. If you find this kind of calm scientific exploration helpful, you can leave a like and subscribe to the channel. It helps more listeners find this quiet corner of physics, especially those who enjoy learning without being hurried through every idea. You can also share where you're listening from, because plasma may be universal, but bedtime is still very local. Somewhere it is early evening, somewhere else it is well past midnight, and above every location, whether visible or not, there is a universe filled with glowing, charged matter. Most of us learn early in school that matter comes in three familiar states. Solids keep their shape, liquids flow while keeping roughly the same volume, gases spread out to fill the space available to them. This is a useful beginning, but nature is not required to stop where an introductory textbook stops. Matter can take many forms under different conditions. Plasma is often called the fourth state of matter, not because there are only four, but because it is the next major state commonly introduced after solids, liquids, and gases. The basic sequence is easy to picture. Give a solid enough heat, and it may melt into a liquid. Add more energy, and the liquid may become a gas. Continue adding energy, and collisions between particles become more violent. Eventually, some electrons can be knocked away from their atoms. Once enough charged particles are present and able to interact collectively, the gases become plasma. This description is useful, but it can also create a misleading image. It may sound as though every plasma must be unimaginably hot. Many plasmas are extremely hot, especially inside stars and fusion experiments. But temperature is not the only factor that matters. A plasma can form when electric fields accelerate electrons strongly enough to ionize atoms, even when the entire material is not uniformly hot. This is why some laboratory plasmas are described as cold plasmas. The electrons may carry a great deal of energy while the heavier particles remain much cooler. Under carefully controlled conditions, such plasmas can interact with skin, food, medical instruments, and delicate materials without burning them. So plasma is not defined simply as hot gas. It is defined more by what the particles are doing and how they influence one another. The presence of free charge changes everything. An ordinary gas responds mainly through collisions, pressure, and temperature. Plasma responds through electric and magnetic forces over much greater distances. A movement in one region can affect particles far away. Groups of charged particles can create waves, currents, filaments, sheets, and rotating structures. Instead of behaving only as countless separate atoms flying about, the plasma can act collectively. Imagine a crowded room where everyone is wearing noise-cancelling headphones. People move around, bump into one another, and respond mostly to what happens nearby. That is not a perfect model of a gas, but it gives us the idea of local interaction. Now imagine that everyone removes the headphones and begins reacting to announcements, music, lights, and the movement of the entire crowd. A small event on one side of the room can influence behaviour across the whole space. Plasma is not a crowd of people, of course, and electrons are not waiting for a public announcement, but the important change is similar. The particles are connected by fields that extend beyond individual collisions. This collective behaviour is one reason plasma can be difficult to describe. It does not merely sit in a container and wait politely to be measured. It can become unstable. It can form narrow channels. It can twist around magnetic field lines. It can separate into regions with different temperatures and densities. It can generate its own electric and magnetic fields, which then influence the motion of the plasma that created them. Physicists sometimes spend years studying one particular instability, which is a scientific way of saying that the plasma keeps doing something inconvenient and refuses to stop. Even the simplest question, what is plasma, has more than one useful answer. A basic answer says it is an ionized gas. A better answer adds that the charged particles show collective behaviour. A more detailed answer considers how many particles are ionized, how effectively electric fields are screened, how often particles collide, and whether the system behaves over large scales as a connected charged medium. The deeper we look, the more plasma becomes not one single substance, but a broad family of physical systems. A candle flame is sometimes described as plasma, although the amount of ionization is small. A fluorescent lamp contains a low-pressure plasma that produces ultraviolet light, which then causes a coating inside the tube to glow. Neon signs use electrical discharges through gases to create coloured light. Lightning forms a hot channel of ionized air. The upper atmosphere contains layers of charged particles created mainly by solar radiation. The sun is made mostly of plasma. So are other stars. Vast clouds of plasma drift between stars and galaxies. Streams of charged particles flow away from the sun as the solar wind. Around Earth, those particles interact with the planet's magnetic field and help produce auroras. This means that the solid surfaces and liquid oceans familiar to us are not typical of the universe as a whole. They are typical of our immediate environment. When astronomers look outward, much of the visible matter they observe is plasma. Stars shine because of processes taking place in hot, dense plasma. Glowing nebulae reveal regions where atoms have been ionized by radiation from nearby stars. Enormous jets from active galaxies carry plasma across distances that are difficult to imagine. Even where space looks empty, it often contains thin plasma threaded by magnetic fields. That raises a pleasant little reversal. On Earth, plasma can feel exotic. In the universe, solids and liquids may be the unusual local arrangement. We live on a relatively cool rocky surface, surrounded by air that is mostly neutral, and so we naturally build our basic understanding of matter from stones, water, tables, clouds, kettles, and the occasional biscuit that has remained in the cupboard longer than expected. From that point of view, plasma appears to be an extra category. From the point of view of a star, we are the strange ones. The familiarity of solids and liquids also makes it tempting to imagine plasma as a substance with a single appearance. Water looks recognisably like water in many ordinary situations. Steel looks like steel. Plasma has no one standard look. It may glow red, blue, violet, white, or not visibly glow at all. It may be dense or extremely thin. It may exist for a tiny fraction of a second or remain stable for billions of years. It may occupy a narrow spark between two contacts or fill a region larger than a planetary system. Its colour, when it does glow, depends on the particles present and the energy moving through them. Excited electrons can later return to lower energy states, releasing light at particular wavelengths. Different atoms produce different patterns of light. This is why electric signs filled with different gases show different colours. It is also why astronomers can study the light from distant stars and nebulae to learn what they contain. The glow is not just decoration. It carries information about the plasma's composition, temperature, density and motion. There is something especially useful about charged particles producing light, because it allows us to study environments we cannot visit. No probe can travel into the centre of the Sun and return with a convenient sample in a labelled container. Instead, physicists examine the light and particles that escape. They compare observations with models of how plasma behaves under intense heat, pressure, gravity and magnetic fields. The results help explain solar flares, sunspots, stellar winds, and the long lives of stars. Closer to home, plasma affects technology in ways that often remain hidden. Modern electronics can be manufactured using plasma processes that etch tiny patterns into materials. Plasma can clean surfaces, modify coatings, sterilize equipment, and help produce certain chemicals. It is used in some forms of cutting and welding, because a focused plasma jet can transfer a large amount of energy to a small area. Researchers are studying plasma for medicine, agriculture, pollution control, spacecraft propulsion and energy production. Fusion energy receives the most attention because it promises something extraordinary. Stars release energy by joining light atomic nuclei under conditions of enormous temperature and pressure. Scientists on Earth are trying to create controlled fusion in plasma and capture more useful energy than the process requires. The idea sounds simple when placed in one sentence. Heat fuel until it becomes plasma, hold it together, allow nuclei to fuse and collect the energy. The difficulty is that plasma hot enough for fusion has no interest in remaining close to ordinary material. Any container that touched it directly would be damaged. Researchers therefore use magnetic fields, rapid compression, or other techniques to confine and control it. This is where plasma begins to reveal its difficult personality. Because it contains charged particles, magnetic fields can guide its motion. That is helpful. Because the plasma can also create currents and fields of its own, it can develop waves and instabilities that interfere with confinement. That is less helpful. Building a fusion device is not like putting hot soup in a stronger bowl. It is more like trying to hold a restless, electrically active cloud, using invisible forces while the cloud changes the forces around it. Plasma physics therefore sits at the meeting point of many subjects. It includes thermodynamics, electromagnetism, fluid behaviour, atomic physics, statistical mechanics, and sometimes relativity. A plasma may behave like a fluid on one scale and like a collection of individual particles on another. Collisions may dominate in one environment and barely occur in another. Magnetic fields may be unimportant in one experiment and control almost everything in another. This variety is the reason simple definitions should be treated as doors rather than complete rooms. Saying plasma is ionized gas lets us enter the subject. It tells us where to look. It does not yet explain why plasma can carry currents, produce waves, form glowing filaments, release sudden bursts of energy, or organize itself into structures across enormous distances. It does not explain why magnetic fields can trap it, twist it, accelerate it, or sometimes fail to control it completely. It does not explain how auroras move like curtains, why lightning branches, or why the sun's outer atmosphere reaches such high temperatures. Still, we do not need to rush toward every complication at once. The first useful idea is simply that ordinary matter changes when enough energy is supplied. Atoms that once travelled as electrically balanced units begin to lose electrons. Those electrons are then free to move separately. The remaining ions carry positive charge. The mixture may still contain many neutral atoms, especially in a weakly ionized plasma, but even a relatively small charge population can change the behaviour of the whole system. Electric charge is the beginning of the difference. Opposite charges attract, like charges repel. Moving charges create magnetic effects. Electric and magnetic fields push particles in directions that depend on their charge and motion. Since electrons are much lighter than ions, they often respond more quickly. This difference in response can create currents, layers, and imbalances that the plasma then tries to correct. The result is motion that can be orderly for a while, chaotic for a while, and occasionally both depending on how closely you look. You might wonder whether plasma should be thought of as dangerous. The honest answer is that it depends entirely on the plasma. Lightning is dangerous. The plasma inside the sun would be more than inconvenient. A tiny controlled plasma used to treat a surface can be safe enough to handle with proper equipment. The word describes a state of matter, not a threat level. Water can be a drink, a cloud, a flood, or part of a cutting jet. Plasma also appears across a wide range of conditions. You may also wonder whether fire is plasma. This question has a slightly untidy answer. Some flames contain enough ions and free electrons to show limited plasma behaviour, particularly at high temperatures or in certain chemical conditions. Many ordinary flames are only weakly ionized, so calling every flame a plasma can be too simple. A flame is mainly a region of hot gases undergoing chemical reactions. It may include plasma, but the two words are not interchangeable. The same caution applies to glowing objects in general. Not everything that glows is plasma, and not every plasma glows visibly. A hot piece of metal can glow because of its temperature. A chemical reaction can produce light. Certain living organisms glow through biochemical processes. Plasma often emits light, but light alone does not define it. Perhaps the most important thing to carry forward is that plasma is matter whose internal electrical structure has become active on a larger scale. In a neutral gas, positive and negative charges are mostly bound together inside atoms and molecules. In plasma, some of those charges are free. Once free, they respond to fields, create currents, exchange energy, and influence one another across the material. The gas has not merely become hotter, it has gained a new set of behaviours. That is why plasma deserves its own place in physics. It is not an unusual footnote added after solids, liquids, and gases. It is essential for understanding stars, space, lightning, modern manufacturing, and the search for fusion energy. It connects the very small motion of electrons with structures that stretch across planets and galaxies. It can be created in a glass tube on a laboratory table, yet the same basic principles help describe the sun above us. For now, there is no need to remember every term. You only need the central picture. Begin with a gas, give its particles enough energy, or place them in a strong enough electrical environment. Some electrons break free from their atoms. The material becomes electrically active. Individual particles still collide and move, but now fields connect their behaviour. Light may appear, currents may flow, magnetic forces may guide the motion. A familiar gas has crossed into a state that can behave in surprisingly unfamiliar ways. And that brings us to the next question. If plasma begins with a gas receiving enough energy, what exactly happens during that change? To understand plasma properly, we need to slow the process down and follow an atom as its calm, electrical balance begins to come apart. The change begins with something that sounds simple, energy enters a gas. That energy may arrive as heat, an electric field, intense light, radiation, or a fast-moving particle. The atoms and molecules in the gas begin moving more quickly, colliding more often, and carrying more energy into each collision. Most of the time, nothing dramatic happens. The particles bounce apart, change direction, and continue on their way. If enough energy is transferred in the right kind of collision, however, an electron can be knocked free from an atom. That single event is called ionization, and it is the first step toward plasma. An atom normally contains a positively charged nucleus surrounded by negatively charged electrons. The total positive and negative charge usually balances, so the atom as a whole is electrically neutral. The electrons are not attached like tiny balls glued to the nucleus. They exist in allowed states controlled by quantum physics, and different electrons require different amounts of energy to remove. The outer electrons are generally easier to separate than those held closer to the nucleus. When an atom receives enough energy to lose one of those outer electrons, the atom is left with more positive charge than negative charge. It has become a positive ion. The freed electron does not disappear. It moves through the gas, carrying negative charge and often a considerable amount of energy. Now the gas contains at least 3 kinds of participants. There are neutral atoms or molecules, positive ions, and free electrons. At first, there may be only a tiny number of charged particles among a much larger number of neutral ones. Even so, those few charges can begin changing the behavior of the gas. Picture a quiet room filled with people sitting in separate chairs. Everyone is present, but there is little communication beyond the occasional glance or polite cough. Then one person stands up and begins walking around. That movement attracts attention. Someone else responds. A third person follows. Soon the room is no longer a collection of still individuals. It has become an active crowd. Ionization is not a social event, and electrons are not trying to start a meeting. But one energetic particle can create conditions that lead to more charged particles and much more activity. A free electron moving through the gas may collide with another neutral atom. If the electron has enough energy, it can knock out another electron. Now there are 2 free electrons and 2 positive ions. Those electrons may accelerate in an electric field and strike more atoms. The process can repeat. Under the right conditions, a small number of charged particles can grow into a much larger population. Physicists call this an ionization avalanche. This is one way an electrical spark begins. Before the spark, the air between 2 points is mostly neutral and does not conduct electricity very well. A strong electric field accelerates the few free electrons that are already present. Those electrons may come from natural background radiation, ultraviolet light, or other ordinary sources. As they gain speed and collide with air molecules, they create more ions and electrons. The air becomes increasingly conductive. A narrow channel forms, current flows, and a flash of light appears. The flash is not the electricity itself becoming visible. What we see is light released by atoms and molecules that have absorbed energy. Some collisions remove electrons completely, but others simply lift electrons into higher energy states without freeing them. These excited electrons soon return to lower states and release the extra energy as light. Different gases release different colours because their atoms and molecules have different allowed energy changes. This is why a gas discharge tube can glow so clearly. Place a gas at low pressure inside a glass tube, apply a suitable electric voltage, and free electrons begin accelerating through the gas. They collide with atoms, excite them, and sometimes ionize them. The excited atoms release light. Neon produces a familiar reddish-orange glow. Other gases and mixtures can produce blue, green, violet, white, and many other colours. The glowing signs seen above shops and restaurants are small demonstrations of gas becoming electrically active. The pressure of the gas matters a great deal. In a dense gas, particles are close together, so an electron collides frequently. Frequent collisions may prevent it from gaining much energy between impacts. In a very thin gas, the electron can travel farther and accelerate more, although there may be fewer atoms available to strike. A working plasma device often requires a useful balance between these conditions. Too many collisions can slow the electrons. Too few can make ionization difficult to sustain. Temperature also needs careful explanation. In everyday life, temperature gives us a sense of how hot something feels. In physics, it is related to the average energy of the particles, but a plasma may contain several groups of particles with very different average energies. Electrons are much lighter than ions, so electric fields can accelerate them quickly. The electrons may become highly energetic while the heavier ions and neutral particles remain comparatively cool. That creates what is commonly called a cold plasma. The name can be misleading because the electrons are not necessarily cold. Some of them carry enough energy to ionize atoms, break chemical bonds, and produce reactive particles. The gas as a whole, however, may remain near room temperature because the heavy particles have not received as much energy. This makes cold plasma useful for treating materials that could not survive the heat of a flame or a furnace. Cold plasma can be used to sterilize some medical tools, clean surfaces, change how materials interact with liquids, and assist certain manufacturing processes. Researchers are also exploring carefully controlled plasma for wound treatment and other medical applications. The aim is not to place hot stellar matter near the body. It is to produce a low-temperature mixture containing energetic electrons and chemically active particles. Plasma is a broad category, and one member of the family can behave very differently from another. At the other extreme, thermal plasmas have particles that are much closer to sharing a common high temperature. Arcs used in welding and cutting are examples. In an electric arc, current passes through ionized gas between electrodes. The plasma becomes extremely hot and can melt metal. Lightning is another thermal plasma. The channel of air inside a lightning bolt is heated so rapidly that it expands violently, creating the pressure wave we hear as thunder. The lightning channel lasts only a short time, but it reveals several important features of plasma. The air begins as a mostly neutral gas. A strong electric field develops between regions carrying different charges. Ionization creates a conductive path. Current flows through that path and heats it intensely. The hot plasma emits light and expands. As the current weakens, electrons recombine with ions, the channel cools, and the air returns toward its neutral state. Recombination is the reverse of ionization. A free electron is captured by a positive ion, restoring a neutral atom or a less highly charged ion. Energy must be released during this process. It may leave as light or be transferred through a collision. If ionization stops and recombination continues, the number of free charge particles falls. Eventually, the plasma may no longer sustain its collective electrical behavior. A plasma therefore does not exist simply because ionization happened once. It must be maintained, or it must last long enough for the charged particles to behave together before recombination removes them. A steady plasma requires some source of energy. In a lamp, an electric supply maintains the discharge. In the sun, enormous temperatures and pressures keep matter ionized. In the upper atmosphere, sunlight provides energy that removes electrons from atoms and molecules. When the energy source changes, the plasma changes with it. Not every atom needs to be ionized. A gas can behave as plasma even when most of its particles remain neutral. This is called a partially ionized plasma. Many plasmas in laboratories, flames, planetary atmospheres, and space fall into this category. Charged particles interact with neutral particles through collisions, while also responding to electric and magnetic fields. The mixture can be complicated because different processes dominate at different times and distances. A fully ionized plasma contains almost no neutral atoms. This is more likely at very high temperatures, where collisions are energetic enough to keep electrons separated from nuclei. The interior of a star is a good example. Hydrogen, the main ingredient in most stars, is stripped into positive nuclei and free electrons. Heavier elements may lose several electrons depending on the temperature and density. An atom can lose more than one electron. After the first electron is removed, the atom becomes a positive ion. Removing another electron usually requires additional energy because the remaining electrons are held more tightly by the now more positive ion. Under sufficiently energetic conditions, many or even all of an atom's electrons can be removed. A heavy ion in a very hot plasma may carry several units of positive charge. These highly charged ions appear in stellar interiors, fusion experiments, and energetic regions of space. Their charge affects how strongly they respond to fields and how they collide with other particles. It also changes the light they can emit and absorb. By examining that light, scientists can identify ions that exist only at particular temperatures. In this way, distant plasma can act as its own thermometer. The phrase ionized gas still leaves an important question. How much ionization is enough? There is no single percentage that separates every gas from every plasma. The answer depends on how the charged particles behave. A small charged fraction may be enough if electric and magnetic forces control the system over useful distances and times. A larger charged fraction may fail to show clear collective behavior if the conditions do not allow the particles to interact in the necessary way. This is why physicists look for more than free electrons. They examine whether the plasma can shield electric disturbances, support waves, carry currents, and respond collectively. If one small region becomes more positive or more negative, the surrounding charged particles move in response. Electrons are attracted toward positive regions and repelled from negative ones. Ions respond in the opposite direction. Their movement tends to reduce large charge imbalances. This shielding is one of the basic properties of plasma. Place an electric charge inside an ordinary vacuum, and its electric influence extends outward over a long distance. Place it inside plasma, and nearby charged particles rearrange themselves around it. Opposite charges gather closer, like charges move away, and the original electric field becomes weaker beyond a certain distance. The plasma acts as though it is wrapping the disturbance in a cloud of compensating charge. The shielding is not perfect at every scale. Very close to a charged particle, its field still matters. Farther away, the combined response of many particles reduces the effect. This tells us something important about collective behavior. A plasma does not merely contain charges. Its charges are mobile enough and numerous enough to reorganize when conditions change. The same mobility lets plasma conduct electricity. In a metal wire, electrons move through a structure of atoms. In plasma, electrons and ions move through a gas-like medium. An electric field pushes negative and positive charges in opposite directions, creating current. The details depend on collisions, temperature, density, and magnetic fields. But the central point is straightforward. Free charge makes electrical conduction possible. A neutral gas is usually a poor conductor because its electrons are bound to atoms and molecules. Increase the electric field enough and the gas may break down. That phrase sounds as though the gas has suffered an emotional crisis, but it simply means the gas becomes conductive through ionization. Once breakdown begins, the current can rise rapidly. This is useful inside lamps and plasma devices, but inconvenient inside electrical insulation. Engineers work hard to prevent unwanted gas breakdown in power systems. High voltage equipment is designed with suitable distances, materials and shapes to reduce strong electric fields. Sharp points are especially troublesome because electric fields can become concentrated around them. This can ionize nearby air and produce a faint discharge called a corona. Corona discharge may glow, make a buzzing sound, create ozone, and slowly damage equipment. Corona discharge also appears naturally around tall objects during strong electrical conditions. Sailors once reported a blue or violet glow around ship masts during storms. This effect became known as St. Elmo's fire. It is not ordinary fire. It is a plasma discharge caused by intense electric fields ionizing the air near pointed structures. The glow may look supernatural on a dark night, although the explanation is firmly electrical. Gas breakdown does not always produce a bright spark. Depending on pressure, voltage, geometry, and gas composition, the discharge may be faint, diffuse, pulsing, or concentrated into an arc. Small changes can produce very different behaviour. Plasma devices are designed around these differences. A fluorescent lamp needs a stable glow discharge. A welding torch needs a concentrated hot arc. A plasma television, when such displays were common, used tiny gas cells that emitted ultraviolet light to excite coloured materials on the screen. The creation of plasma through heat follows a different route but reaches the same basic result. As a gas becomes hotter, its particles move faster on average. Collisions become more energetic. At first, molecules may break apart into simpler molecules or individual atoms. With further heating, electrons begin separating from atoms. The exact temperatures depend on the material and pressure. There is no universal temperature at which every gas suddenly becomes plasma. The transition can be gradual. In a melting solid, we often imagine a clear boundary between solid and liquid. In ionizing gas, the charge fraction may increase steadily as more energy is supplied. At one stage, only a few particles are ionized. Later, charged particles become common. At still higher energy, the gas may become almost fully ionized. The plasma wakes up little by little, rather than responding to a single alarm. That gradual change matters inside stars. A star is not equally hot and dense everywhere. Conditions vary from the core to the surface and beyond into the outer atmosphere. Different elements lose different numbers of electrons in different regions. The plasma's ability to absorb and carry energy changes with ionization. This helps determine how heat and radiation move through the star. In Earth's atmosphere, plasma forms mainly through radiation and particle impacts rather than ordinary heating alone. High above the surface, ultraviolet light and other energetic radiation from the sun strike atmospheric particles and remove electrons. This creates the ionosphere, a set of regions containing free electrons and ions. The ionosphere affects radio communication because charged layers can reflect, refract, or absorb radio waves depending on their frequency and the conditions. The ionosphere changes between day and night. Sunlight creates more ionization during the day. After sunset, recombination reduces some of the charged population, although the process does not happen instantly. Solar activity also changes the ionosphere. Bursts of radiation and charged particles from the sun can disturb it, influencing communication, navigation, and satellite operations. Auroras occur higher in the atmosphere when energetic particles guided by Earth's magnetic field collide with atmospheric atoms and molecules. These collisions excite and ionize the gas. As the particles return to lower energy states, they emit colored light. Oxygen can produce green and red emissions. Nitrogen contributes blue and violet shades. The shifting curtains are shaped by magnetic fields and changing streams of particles. An aurora shows that plasma is not created only by heating something until it glows. Energy can be delivered selectively by radiation, electric fields, or incoming particles. What matters is whether electrons receive enough energy to separate from atoms and whether enough charged particles remain active together. Lasers can also create plasma. A sufficiently intense laser pulse focuses energy into a small region, ionizing matter rapidly. This may produce a bright flash, a tiny expanding plasma, and a pressure wave. Laser-created plasmas are used in research, material analysis, and some forms of fusion experimentation. In one analytical technique, a laser pulse vaporizes and ionizes a minute amount of material. The light emitted by the plasma reveals which elements were present. Microwaves can sustain plasma as well. Energy from the electromagnetic field accelerates electrons, which collide with atoms and maintain ionization. Microwave plasmas are used in processing materials, producing chemicals, and laboratory research. Once again, the source of energy differs, but the basic story remains familiar. Electrons gain energy. Collisions create ions and more electrons. The charged mixture begins behaving collectively. There is also plasma created by mechanical shock. A powerful shock wave compresses and heats a gas so rapidly that ionization occurs. This can happen during explosions, high-speed atmospheric entry, and certain laboratory experiments. A spacecraft returning through the atmosphere moves so quickly that the gas in front of it is compressed and heated into plasma. The glowing sheath around the vehicle can interfere with radio signals, creating a temporary communication blackout. That same plasma sheath helps remind us that temperature describes particle energy, not simply the sensation of warmth. A spacecraft is surrounded by gas whose particles have been driven into extremely energetic conditions. The material glows and conducts electricity. It interacts with radio waves and magnetic fields. The air has not become a different chemical element. Its atoms and molecules have been broken apart, excited, and ionized by intense energy. Once the energy is removed, the plasma does not remain plasma forever. Electrons slow down through collisions. Ions capture electrons. Excited particles release light. The material cools and returns toward a neutral gas. In some cases, this happens almost immediately. In others, low density and limited collisions allow the plasma to persist much longer. Space plasmas can remain ionized at temperatures and densities that would seem surprising on Earth. In very thin regions of space, particles may travel great distances before colliding. Recombination is slow because electrons and ions do not meet often. Radiation and energetic particles may continue supplying ionization. The result is a plasma that can extend across enormous volumes while containing very little matter in any small portion of space. This is another reason not to treat plasma as merely very hot gas. Density, energy supply, collision rate, and time all matter. A thin plasma can have highly energetic particles, but transfer little heat to an object because so few particles strike it. A dense plasma at a similar particle energy can deliver far more heat. The words hot and cold need context. By now, the awakening of gas is becoming less mysterious. It begins when energy changes the internal electrical arrangement of matter. Electrons leave atoms, ions remain behind. New collisions create more charged particles. Recombination removes them. The final state depends on the competition between these processes. If ionization is sustained and the charges act together, the gas takes on the properties of plasma. Yet the story becomes much more interesting once those charges start moving. Electrons and ions differ greatly in mass, speed, and response. They do not drift through the plasma in identical ways. An electric field may send them in opposite directions. A magnetic field may bend their paths. Their separation can create new fields, and those fields can change the motion again. To understand why plasma forms waves, currents, spirals, and glowing structures, we need to follow the separate movements of its positive and negative particles. Once electrons have broken free from their atoms, plasma becomes much more than a hot collection of particles. It becomes a place where positive and negative charges move at different speeds, respond to different forces, and continually influence one another. The ions are heavy and slow to react. The electrons are light and quick. Both are surrounded by electric and magnetic fields, and every movement changes the conditions for the particles nearby. This difference between ions and electrons is the source of much of plasma's unusual behavior. An electron has far less mass than even the lightest positive ion. When the same electric force acts on both, the electron changes its motion much more rapidly. It can accelerate, turn, and respond to a disturbance before the ion has moved very far at all. The ions are not motionless, but compared with the electrons, they often seem patient. Imagine a crowded dance floor, where one group is wearing heavy boots, and the other is wearing socks on a polished surface. When the music changes, the people in socks can turn almost immediately. Those in heavy boots need more time. The two groups are part of the same dance. but they do not move in exactly the same way. That mismatch creates patterns, gaps, waves, and moments when one side appears to lead the other. In plasma, the music is supplied by electric and magnetic fields. An electric field pushes positive ions in one direction and negative electrons in the opposite direction. If the field is steady, the two groups begin drifting apart. This separation creates a new electric field that resists the original movement. The particles then respond to that new field as well. Plasma is constantly adjusting itself in this way. Large separations of charge usually do not last very long. If too many electrons leave one region, that region becomes positively charged and begins pulling electrons back. If too many electrons gather somewhere else, they repel one another and push outward. The plasma tends toward a state in which the positive and negative charges nearly balance over large distances. Physicists call this overall balance electrical neutrality. It does not mean that every tiny location contains exactly the same amount of positive and negative charge at every instant. Small imbalances are always appearing. The electrons may rush ahead, the ions may lag behind, and local electric fields may develop. The important point is that the plasma usually acts to reduce large, lasting imbalances. This restoring behavior can make the electrons oscillate. Suppose a group of electrons is pushed slightly away from the ions. The ions are left behind with a net positive charge, so they attract the electrons back. The electrons move toward them, but because they have momentum, they may overshoot. They then find themselves displaced on the other side and are pulled back again. The result is a rapid back and forth motion. It is rather like pulling a weight attached to a spring and letting go, except that the restoring force comes from electric attraction rather than a metal coil. These oscillations are among the most basic motions in plasma. They show that the particles are not simply wandering independently. A disturbance in charge can make a large population respond together. Electrons can complete this motion extremely quickly because of their low mass. The ions respond more slowly. Over longer periods, however, the ions also move and participate in waves of their own. Some plasma waves involve mainly electrons. Others involve the motion of ions and electrons together. The exact behavior depends on the plasma's density, temperature, magnetic field, and the kinds of particles present. Waves in plasma are not limited to the familiar rising and falling shape seen on water. A plasma wave may be a repeating change in density, electric field, magnetic field, particle speed, or some combination of all of them. The particles do not necessarily travel with the wave. They may move back and forth locally while the disturbance carries energy across the plasma. This is similar to a sound wave passing through air. The air molecules do not travel all the way from a speaker to your ear. They vibrate around their local positions, transferring the disturbance from one region to the next. Plasma can support sound-like waves, but because it contains charged particles, it can also support many other types that ordinary gases cannot. Some waves travel mainly because pressure changes push particles from crowded regions toward less crowded regions. Others are controlled by electric forces. Still others depend strongly on magnetic fields. A single plasma may support several kinds of waves at the same time, each moving at a different speed and carrying energy in a different way. This can make plasma look restless, even when there is no obvious object stirring it. Waves can reflect from boundaries, combine with one another, grow stronger, or fade away. They can transfer energy between particles and move disturbances across great distances. In space, plasma waves help carry energy through the solar wind and through the magnetic environments around planets. Magnetic fields make the dance much more complicated. A charged particle moving through a magnetic field is pushed sideways rather than directly forward or backward. The force bends the path of the particle. Instead of moving in a straight line, it begins circling around the direction of the magnetic field. The electron and the ion circle in opposite directions because they carry opposite charges. The electron makes a much tighter and faster turn because it is lighter. The heavier ion follows a wider, slower path. At the same time, both particles can continue moving along the magnetic field. Their overall paths become spirals wrapped around invisible magnetic lines. These spiraling motions are fundamental to plasma physics. They allow magnetic fields to guide charged particles without physically touching them. A particle may move freely along a magnetic field while being restricted across it. The field acts less like a wall and more like a set of rails. This is why Earth's magnetic field can guide charged particles toward the polar regions. Particles from space enter the planet's magnetic environment and begin spiraling along field lines. Many are redirected around Earth, while some travel toward the upper atmosphere near the poles. There they collide with atmospheric particles and contribute to auroras. The same principle is used in fusion experiments. Hot plasma cannot be allowed to touch the walls of an ordinary container for long. Magnetic fields are arranged to guide the particles along curved paths, keeping much of the plasma away from solid surfaces. The particles spiral around the field and follow it around the machine. Of course, plasma does not always cooperate. The particles collide, drift, form waves, and generate fields of their own. Some particles escape their intended paths. Small disturbances can grow into large instabilities. A carefully designed magnetic cage can begin to leak energy or particles because the plasma finds a motion that the designers had hoped it would overlook. One important detail is that magnetic fields do not provide energy in the same direct way that electric fields do. A magnetic force bends a charged particle's motion, but it does not normally make the particle move faster by itself. It changes direction rather than speed. Electric fields, on the other hand, can accelerate particles and change their energy. When electric and magnetic fields exist together, particles can develop additional drifting motions. The center of a particle's spiral may slowly move across the plasma. Electrons and ions may drift in the same direction, under some conditions and in different directions under others. These drifts can create currents. A current is simply an organized movement of electric charge. In a wire, current is usually carried by electrons moving through a solid material. In plasma, both electrons and ions can contribute. Because they carry opposite charges, their directions and speeds determine the total current. Electrons often carry most of the current because they move more easily. An electric field can produce a rapid electron flow, while the ions respond more slowly. Yet ion motion can still become important, especially in dense plasmas, long-lasting systems, and large structures in space. Currents in plasma create magnetic fields. This means plasma can reshape the magnetic environment that controls it. The particles move because of a field. Their motion creates a current. The current creates another field, and the new field changes the particle motion again. Plasma is both the performer and part of the stage. This feedback is responsible for many of the structures seen in laboratory and space plasmas. Currents can concentrate into narrow channels called filaments. Magnetic forces around those currents can squeeze the plasma inward. The squeezed region may become hotter and denser, which changes its electrical properties and can strengthen the current further. Lightning provides a familiar example of a current concentrated into a narrow plasma channel. The current heats the air, and the channel becomes bright and highly conductive. The current also creates a magnetic field around itself. In more extreme plasmas, magnetic squeezing can become powerful enough to shape and compress large structures. Similar filamentary forms appear in solar plasma, electrical discharges, and certain laboratory experiments. They may twist, split, merge, or move. Their appearance can suggest ropes or threads, although they are not solid objects. They are regions where current, density, temperature, and magnetic field differ from the surrounding plasma. The movement of plasma along magnetic fields can also produce large-scale currents in space. Earth's magnetic environment contains systems of current that connect distant regions. The Sun supports currents in its atmosphere and magnetic loops above its surface. Galaxies and the space between them contain plasma shaped by weak magnetic fields over enormous distances. A magnetic field does not need to be strong in everyday terms to influence a very thin plasma. In space, particles may travel long distances between collisions, so even a weak field can gradually bend their paths. Over enough time and distance, the effect becomes important. Collisions still matter though. Electrons collide with ions, neutral particles, and other electrons. Ions collide with each other and with neutrals. These collisions exchange energy and momentum. They can slow currents, spread heat, and push the plasma toward a more uniform state. When electrons move through ions, collisions resist their motion. This electrical resistance converts organized motion into random particle motion, which means heat. It is similar to the heating of a wire carrying current, although the detailed process is different because the material is plasma. A plasma with frequent collisions may behave in some ways like an electrically conducting fluid. Its large-scale motion can be described without following every particle separately. This is extremely useful because even a tiny amount of plasma contains an enormous number of particles. Tracking each electron and ion would be impossible. Scientists therefore choose different descriptions depending on the problem. For some questions, plasma is treated as a fluid with density, pressure, temperature, current, and fields. For others, the paths of individual particles are essential. A fusion researcher studying particle escape may focus on individual spirals and collisions. An astronomer studying a giant plasma cloud may use a fluid description. Neither view is always complete. Plasma lives between the individual and the collective. A single particle follows local forces, yet the fields producing those forces may be created by the motion of millions of other particles. Large structures emerge from small movements, and those structures guide the particles in return. This circular relationship helps explain why plasma can become unstable. An instability begins when a small disturbance causes changes that reinforce the disturbance instead of reducing it. A slight increase in density may strengthen a current. The stronger current may alter the magnetic field. The changed field may push more particles into the dense region. What began as a tiny fluctuation grows. Not every disturbance grows. Many fade away. The plasma may spread the extra energy, restore charge balance, or damp the motion through collisions. The challenge is determining which conditions produce stability and which allow an instability to develop. In fusion devices, instabilities can make the plasma wobble, ripple, twist, or move toward the wall. Some occur near the edge, others affect the entire confined plasma. Researchers use sensors, magnets, heating systems, and rapid control methods to detect and reduce these motions. The difficulty is not merely technical, it comes from the nature of plasma itself. A hot plasma contains particles moving at many speeds and directions. It supports waves across a wide range of scales. Electric and magnetic fields connect distant regions. Energy can move from large structures into small ones and from small motions back into larger patterns. Turbulence is one result. In ordinary fluids, turbulence appears when smooth flow breaks into irregular swirls and eddies. Plasma turbulence includes those fluid-like motions along with fluctuations in charge, current, and fields. Tiny disturbances can combine into a constantly changing pattern that transports heat and particles. This transport is one reason fusion plasma loses energy. Even when particles are magnetically confined, turbulence can carry heat across the field toward the walls. The losses may be much larger than would be expected from simple collisions alone. Understanding and controlling plasma turbulence is therefore essential to maintaining the extreme conditions required for fusion. Space plasma is turbulent as well. The solar wind is not a perfectly smooth stream. It contains waves, fluctuations, shocks, and changing magnetic fields. As it travels away from the sun, energy moves between different scales. Spacecraft measure these variations directly, allowing scientists to study plasma turbulence in a natural environment. the solar wind also shows how particles and fields can travel together. Plasma flowing away from the sun carries the sun's magnetic field outward. Because the sun rotates, the field becomes wound into a large spiral pattern across the solar system. Planets move through this changing plasma and magnetic environment. When a strong disturbance reaches Earth, it can compress and shake the planet's magnetic field. Energy enters the surrounding plasma, currents strengthen, and particles are accelerated. The result may be intense auroras and disturbances in technology. Satellites can be affected, radio communication can change, and currents may be induced in long electrical systems on the ground. All of this begins with the separate responses of ions and electrons. Their different masses and charges allow electric fields, currents, waves, and magnetic structures to form. If they moved in perfect agreement at every instant, plasma would lose much of its character. There is another important process that occurs when electrons and ions exchange energy. Electrons may be much hotter than ions, especially in a recently created or low-pressure plasma. Through repeated collisions, they gradually transfer some of their energy to the heavier particles. The temperatures begin moving toward one another. The rate of this energy exchange depends on density, particle type, and other conditions. In thin plasma, collisions may be so rare that electrons and ions remain at different temperatures for a long time. This is common in space. A single value called the temperature may not be enough to describe the entire plasma. Different groups of electrons can also have different energies. Most may move at moderate speeds, while a smaller population travels much faster. These energetic particles can have a large effect. They may create additional ionization, escape confinement, emit strong radiation, or trigger instabilities. Some electrons can be accelerated repeatedly by electric fields and collisions until they move at extremely high speeds. In certain conditions, the faster they become, the less effectively ordinary collisions slow them. This can lead to a runaway population. In fusion devices, runaway electrons can carry enough energy to damage internal components if they strike the wall. The sun and other space environments accelerate particles through several mechanisms. Electric fields can push them directly. Waves can transfer energy to particles whose motion matches the wave in the right way. Magnetic fields can rearrange and release stored energy. Shocks can reflect particles back and forth, increasing their speed. One of the most dramatic magnetic processes is magnetic reconnection. Plasma often contains regions where magnetic fields point in different directions. Under certain conditions, the field arrangement changes rapidly. Magnetic energy is converted into particle motion, heat, and radiation. The phrase magnetic field lines reconnect is a useful picture, but the physical process involves currents, electric fields, and particle motion in a small region, where the usual link between plasma and magnetic field changes. Outside that region, the plasma may move as though it is attached to the magnetic structure. Inside it, particles can cross and rearrange the field. Magnetic reconnection powers solar flares and contributes to eruptions from the sun. It also occurs in Earth's magnetic environment. When magnetic fields carried by the solar wind interact with Earth's field, reconnection can transfer energy into the surrounding plasma. That energy may later be released in the region behind Earth, accelerating particles toward the atmosphere. The sudden release can create bright auroral displays. Charged particles follow magnetic paths downward and collide with oxygen and nitrogen high above the surface. Their energy excites those atmospheric particles, which later release light. Even here, the dance of ions and electrons is not visible directly. We do not see the spiraling paths or the changing electric fields. We see the light produced when the moving particles transfer energy to atoms and molecules. Plasma reveals its hidden motion through colour. The same is true in laboratory tubes, welding arcs, lightning and stars. The glow is a record of collisions and energy changes. Some particles are ionized, others are excited without losing electrons. Electrons fall back into lower energy states. Ions capture free electrons. Each process can release light with its own pattern. To understand why one plasma glows red while another appears blue, green, violet, or white, we need to look more closely at what happens inside atoms after a collision. The motion of free charge creates the plasma, but the light comes from the precise ways that atoms and ions store and release energy. The light begins inside atoms and ions after they have taken energy from moving electrons. A collision may not be strong enough to remove an electron completely. Instead, it can push one of the bound electrons into a higher energy state. The atom is then described as excited. It cannot usually remain in that condition for long. The electron soon returns to a lower state, and the stored energy leaves as a small packet of light. That packet has a particular amount of energy, which means it has a particular colour, or a colour outside the range human eyes can see. The colour is not chosen at random. It depends on the difference between the two energy states inside the atom. Since every type of atom has its own internal structure, every element produces its own collection of colours. This gives glowing plasma a recognisable signature. Hydrogen does not produce exactly the same pattern as helium. Neon does not behave exactly like argon. Oxygen and nitrogen each have their own characteristic emissions. A plasma may contain several elements, several types of ion, and particles at many different energies, so the final glow can be a mixture of many separate contributions. The colours we see are therefore reports from the particles themselves. They reveal what is present, how much energy is being transferred, and sometimes how the plasma is moving. A glowing tube in a laboratory and a distant cloud in space may look very different in size, but the same basic process produces much of their light. Electrons collide with atoms and ions. Bound electrons are excited. They return to lower states. Light is released. A neon sign is one of the clearest everyday examples. Despite the common habit of calling every coloured sign neon, genuine neon gas usually gives a reddish-orange glow. Other colours often come from different gases, coloured glass, or glowing coatings. Argon mixed with a small amount of mercury can help produce blue or violet light. Helium may produce pinkish or yellowish shades. The exact result also depends on pressure, electric current, and the design of the tube. Inside the sign, an electric field accelerates free electrons. Those electrons collide with gas atoms and transfer energy to them. Some atoms become ionized, supplying more free electrons and helping the discharge continue. Others become excited and release visible light. The glass tube keeps the gas at a controlled pressure and prevents ordinary air from mixing with it. The gas pressure is much lower than normal atmospheric pressure. This gives electrons enough room to accelerate between collisions. If the particles were packed too closely, the electrons would strike atoms before gaining the energy needed for useful excitation and ionization. If the gas were much thinner, collisions might become too rare to produce a bright, steady glow. The electric current must also be controlled. Too little current and the plasma may fade or disappear. Too much current and the gas can become very hot, changing the discharge into a more intense arc. A sign maker wants a stable glow that remains bright without overheating the tube. Fluorescent lamps use a related process, although most of the light created directly by the plasma is not visible. The discharge contains mercury atoms that release a large amount of ultraviolet radiation. Human eyes cannot see ultraviolet light, so the inside of the tube is coated with substances called phosphors. These materials absorb the ultraviolet radiation and release visible light. The final colour depends on the mixture of phosphors. By combining materials that emit different parts of the visible range, manufacturers can produce light that appears warm, cool, or close to daylight. The plasma creates the ultraviolet radiation, and the coating converts it into the light that fills the room. This two-stage process explains why the tube does not simply show the natural colour of the gas inside. The visible glow comes mainly from the coating. A similar idea is used in other lighting systems, where plasma produces radiation that is then transformed into a more useful form. Older plasma display screens contained millions of tiny cells filled with gas. Each cell acted like a very small discharge tube. Electric signals ionized the gas and produced ultraviolet radiation. That radiation excited red, green, or blue phosphors. By controlling the brightness of the cells, the screen produced a complete image. The word plasma in plasma display referred to the ionized gas inside those cells. It did not mean that the screen was filled with material as hot as the sun. The amount of plasma was tiny, and the process was carefully controlled. Even so, the basic physics belonged to the same broad family as lightning, fluorescent lamps, and glowing gas clouds in space. A plasma does not always need separate atoms to create light. Free electrons can also emit radiation when their motion changes. An electron travelling near a positive ion is pulled from its original path. As it accelerates and changes direction, it can release radiation. This process becomes especially important in hot, dense plasmas. The radiation produced in this way covers a broad range rather than a few narrow colours. It can include visible light, ultraviolet radiation, and higher energy forms depending on the conditions. Very hot laboratory plasmas and astronomical plasmas can produce strong radiation through the motion of electrons near ions. Electrons moving in magnetic fields can also emit light. Since the magnetic field bends their paths, the electrons are continually changing direction. Energetic electrons spiraling around magnetic fields may release radio waves, visible light, or even more energetic radiation. The exact type depends on how fast the electrons are moving and how strong the magnetic field is. This process is common in space. Some glowing regions around stars, galaxies, and collapsed objects contain electrons moving at nearly the speed of light through magnetic fields. Their radiation can travel across enormous distances before reaching telescopes on Earth. It tells astronomers that energetic charged particles and magnetic fields are present even when the plasma itself cannot be sampled directly. Not every glow from plasma has the same origin. Some light comes from excited atoms. Some comes from ions capturing electrons. Some is produced when free electrons are deflected by ions. Some appears because charged particles are spiraling in magnetic fields. A single plasma can produce several of these forms of radiation at once. Recombination is particularly important when plasma begins cooling. A positive ion captures a free electron. The electron may initially enter a high-energy state and then move downward through several lower states. Light can be released at each step. The resulting pattern can help identify the ion and reveal the physical conditions in the plasma. Large glowing clouds around young, hot stars are often powered by this process. Intense ultraviolet radiation from the stars ionizes surrounding hydrogen gas. Free electrons later recombine with positive hydrogen ions. As the electrons move through the allowed energy states, the gas emits characteristic colours. One strong hydrogen emission falls in the red part of visible light, which is why many star-forming regions appear red in astronomical images. The images may be adjusted to make faint structures easier to see, but the underlying emission is real. It comes from hydrogen atoms rebuilding themselves after ionization. Other elements add their own colours. Oxygen ions can produce green or bluish emissions. Sulfur and nitrogen contribute red and orange light. By separating the light into its component wavelengths, astronomers can determine which atoms and ions are present. This separation is performed with instruments that spread light into a spectrum. A simple rainbow shows a continuous range of colours, but glowing gases often produce bright lines at specific positions. Each line corresponds to a particular energy change within an atom or ion. These spectral lines work like identifying marks. A scientist can compare an unknown spectrum with known laboratory measurements. If the positions match those of hydrogen, helium, oxygen, iron, or another element, the element can be identified. This can be done even when the source is many light years away. The strength of the lines gives further information. Some lines become bright only at particular temperatures or densities. Certain ions can exist only when collisions are energetic enough to remove several electrons. Finding those ions tells scientists that the plasma reached very high temperatures. The relative brightness of different lines can reveal how often particles collide and how rapidly energy is being transferred. It can also show whether the plasma is being heated by radiation, electric current, shocks, or another process. A spectrum is not merely a list of colours, it is a record of the physical events taking place inside the plasma. Motion changes the observed light as well. When a glowing plasma moves toward an observer, its spectral lines shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. The amount of shift reveals the speed along the line of sight. Astronomers use this effect to measure the movement of plasma on the Sun, inside nebula, and around distant stars and galaxies. Opposite sides of a rotating structure may show shifts in different directions. Material flowing outward may produce another pattern. Sudden eruptions can be tracked through rapid changes in the spectrum. Temperature also broadens spectral lines. Particles in a hot plasma move in many directions at different speeds. Some approach the observer while others move away. Their individual shifts blend together, making the line wider. Measuring that width can provide an estimate of particle temperature. Additional broadening may come from collisions, turbulence, electric fields, and magnetic fields. Careful analysis allows scientists to separate some of these effects. A thin mark in a spectrum can therefore reveal temperature, motion, density, magnetic conditions, and composition. This is especially useful because plasma is often difficult to touch with an instrument. A probe placed inside a hot plasma may melt, disturb the plasma, or survive only briefly. Space plasmas may be too distant or too large to sample fully. Light allows the plasma to be studied without direct contact. Laboratory researchers also use emitted light to monitor plasma in real time. A manufacturing system may need the correct mixture of reactive particles. Changes in colour or spectral lines can show whether the process is stable. A fusion experiment may use light and other radiation to estimate temperature, detect impurities, and observe energy losses. Impurities can have a large effect on glowing plasma. Suppose atoms from a metal wall enter a hot fusion plasma. Those heavy atoms contain many electrons and can produce numerous forms of radiation. Energy that should remain in the plasma may leave as light. Enough contamination can cool the plasma and interfere with fusion conditions. This creates an awkward situation. The glow can be useful for diagnosis, but excessive radiation may indicate that valuable energy is escaping. A bright plasma is not automatically an efficient plasma. Sometimes brightness shows successful heating. In other cases, it shows that the plasma is losing energy more quickly than desired. The colour visible to human eyes can also be a poor guide to total energy. A plasma may emit much of its radiation in ultraviolet light, radio waves, or more energetic wavelengths that we cannot see. It could look faint while producing strong invisible radiation. Proper instruments are needed before deciding that a dim plasma is harmless. Lightning demonstrates this clearly. The channel appears bright white because it is extremely hot and produces a broad range of visible light. It also emits radio waves, ultraviolet radiation, and other forms of energy. The visible flash is only one part of the event. The white appearance comes from many overlapping emissions and the high temperature of the channel. Air contains mostly nitrogen and oxygen, along with smaller amounts of other gases. During a lightning strike, molecules are broken apart, atoms are excited and ionized, electrons move through intense fields, and the hot channel radiates strongly. The light arrives before the thunder because light travels far faster than sound. The thunder is produced when the heated channel expands rapidly and creates a pressure wave. The glow and the sound have the same energetic event behind them, but they reach us through different physical processes. Smaller sparks behave in a similar way. Touch a metal object after walking across a carpet, and a brief discharge may jump through the air. The electric field ionizes a narrow path. Electrons accelerate, atoms become excited, and a tiny flash appears. The amount of plasma is small and lasts for very little time, yet it follows the same basic sequence as a much larger discharge. A candle flame can produce light through several mechanisms. Hot soot particles glow because of their temperature. Excited molecules created by chemical reactions emit particular colours. A small number of ions and electrons may also be present. The yellow part of an ordinary candle flame mainly comes from hot soot, rather than strong plasma emission. A clean blue flame behaves differently. Its light comes more from excited molecules and short-lived chemical species. The gas may be weakly ionized, but describing the entire flame simply as glowing plasma would leave out much of the chemistry. Fire and plasma overlap in some conditions without being the same thing. Auroras provide a gentler and much larger example of excitation. Energetic charged particles enter the upper atmosphere along magnetic paths and collide with oxygen and nitrogen. These atmospheric particles absorb energy, then release it as light. Green auroral light commonly comes from excited oxygen at certain altitudes. Red oxygen emission can appear higher in the atmosphere, where collisions are less frequent. Nitrogen and ionized nitrogen contribute blue, purple, and reddish colours. Altitude matters because excited particles need time to release their light. In denser air, collisions can remove the energy before light is emitted. Higher in the atmosphere, the air is thinner, so some excited states survive long enough to produce colours that would be suppressed at lower heights. This helps create the layered appearance of auroral displays. A green curtain may have a red upper region or a purple lower edge. The colours are connected to particle energy, atmospheric composition, altitude, and collision rate. The shape of the aurora is controlled by magnetic fields and moving plasma around Earth. The light traces where energetic particles enter the atmosphere. It allows us to see part of an invisible magnetic system that stretches far into space. Glowing plasma can also change colour as conditions change. Increasing the current may raise the electron energy and excite different states. Changing the pressure alters collision rates. Adding another gas introduces new spectral lines. Cooling the plasma allows recombination to become more important. This sensitivity makes plasma lighting both useful and demanding. A stable colour requires control over gas composition, pressure, current, temperature, and the condition of the container. Small traces of contamination can add unwanted emissions. The same sensitivity is valuable in analysis. Scientists can place a small sample into a hot plasma, where atoms from the sample become excited and emit light. The spectrum then reveals which elements are present. This method can detect very small amounts of material. Plasma-based analysis is used in environmental testing, geology, medicine, manufacturing, and many other fields. A sample of water may be tested for metals. A piece of rock may be examined for its elemental composition. Industrial materials can be checked for impurities. The plasma acts as an energetic environment that turns hidden composition into measurable light. The glow is therefore more than an attractive side effect. It is one of the main ways plasma communicates its condition. Colour shows that energy is moving through atoms and ions. Spectral lines reveal identity. Brightness gives clues about particle populations. Shifts in widths show motion and temperature. There are limits to what light alone can tell us. Different combinations of conditions can sometimes produce similar emissions. Dust, absorption, and viewing angle may alter what reaches an observer. A complete diagnosis often combines light with measurements of particles, electric fields, magnetic fields, and radio waves. Even with those limits, plasma light has transformed our understanding of the universe. Nearly everything known about stars began with radiation arriving at Earth. Their surfaces cannot be sampled directly, yet their light reveals elements, temperatures, motion, magnetic activity, and stages of development. The sun appears as a smooth glowing disk to the unaided eye, but specialized instruments reveal loops, jets, dark filaments, bright active regions, and sudden eruptions. Each feature involves plasma responding to magnetic fields and releasing radiation in different ways. Some of the hottest solar plasma is not best observed in visible light. It emits strongly at shorter wavelengths. Images made with those wavelengths reveal the Sun's outer atmosphere, where plasma follows enormous magnetic arches and changes rapidly during eruptions. Beyond the Sun, glowing plasma fills the space around dying stars, newborn stars, exploded stars, and active galaxies. Some regions shine because nearby radiation keeps them ionized. Others glow because shockwaves heat and compress them. Still others are powered by fast particles moving through magnetic fields. The colours may differ, but the underlying message remains consistent. Charged particles have gained energy. They are colliding, accelerating, recombining, and changing state. Light carries the evidence outward. A glowing sign outside a quiet shop and a bright cloud around a distant star are not identical systems. Their temperatures, densities, sizes, and energy sources differ enormously. Yet both show what happens when gas becomes electrically active, and its particles begin releasing energy as radiation. Looking farther outward makes plasma seem less like a special laboratory substance, and more like the normal visible material of the cosmos. The night sky is dark between the stars, but the stars themselves, the winds leaving them, the clouds around them, and many of the most energetic objects beyond them are made from moving charged matter. To see why plasma dominates so much of what shines above us, we need to leave the glass tube and follow the glow into lightning, the sun, and the space between worlds. The glass tube gives us a controlled view of plasma, but nature rarely keeps things so tidy. Outside the laboratory, plasma appears across an enormous range of sizes and energies. It can last for less than a second in a spark, remain active for minutes inside a lightning storm, or continue for billions of years inside a star. It can be dense enough to release intense heat, or so thin that only a few particles occupy a large volume of space. The common feature is not appearance or temperature. It is the presence of free charged particles that respond together to electric and magnetic fields. Lightning is one of the most familiar natural plasmas on Earth. A storm cloud contains water droplets, ice crystals, and moving air. As these materials collide and separate, electric charge becomes unevenly distributed. Different parts of the cloud can develop different charges, and the ground below may respond by gathering an opposite charge near the surface. The electric field between these regions grows stronger. Air normally resists the flow of electric current because most of its molecules are neutral. If the field becomes strong enough, however, the few free electrons already present begin accelerating. They strike air molecules and create more free electrons and positive ions. The process spreads through the air, forming narrow paths of ionized gas. A lightning strike does not usually begin as one smooth line travelling directly from the cloud to the ground. It develops through branching steps. A faint channel moves through the air in short advances, testing different routes as ionization spreads. At the same time, electrical activity may rise from tall objects on the ground. When the paths connect, a much stronger current flows. The bright flash we see is produced when that current heats the ionized channel. The temperature rises very rapidly, and the air expands with great force. This expansion creates the pressure wave that becomes thunder. The light reaches us almost immediately, while the sound moves much more slowly. That delay lets us estimate how far away the strike occurred. The plasma channel does not remain active for long. As the current falls, the gas cools. Electrons recombine with ions and the air returns toward its neutral state. Some lightning flashes contain several rapid current pulses along the same route, which is why the light may appear to flicker. The branching shape is not decorative. It reflects the way ionization develops through an uneven atmosphere. Temperature, humidity, dust, air movement, and local electric fields all influence the path. The plasma follows routes where electrical breakdown can continue, and those routes change from moment to moment. Lightning also occurs in volcanic clouds, large forest fires, dust storms, and the atmospheres of other planets. Any environment that separates enough charge and creates a strong enough electric field may produce a discharge. Spacecraft have detected lightning on several worlds, including giant planets with thick atmospheres. The details differ from Earth, but the general sequence remains familiar. Charge separates, a field grows, gas becomes ionized, and current flows through plasma. Above ordinary thunderstorms, other forms of electrical discharge can briefly appear. Some spread upward into the upper atmosphere as red or blue flashes. These events may cover much greater distances than a normal lightning channel, although they are often faint and short-lived. They show that a storm can disturb electrical conditions far above the clouds. Earth also contains plasma where there are no thunderstorms at all. High in the atmosphere, sunlight removes electrons from atoms and molecules, producing the ionosphere. This region changes with the time of day, the season, solar activity, and location. It can influence radio signals by bending, reflecting, or absorbing them. The ionosphere is only one part of Earth's larger plasma environment. The planet is surrounded by a magnetic field that extends far into space. Charged particles become trapped, guided, and redirected within this field. Some regions contain belts of energetic particles, others carry large electrical currents. The whole system is shaped by its interaction with plasma flowing outward from the Sun. That outward flow is called the solar wind. It is a continuous stream of electrons, ions, and magnetic field moving away from the Sun. It does not behave like ordinary wind in Earth's atmosphere. It is far thinner, much faster, and electrically active. Even though the number of particles in a small volume is low, the solar wind fills an enormous region. The source of this wind is the Sun's outer atmosphere. The visible surface of the Sun is already extremely hot, but the outer atmosphere reaches even higher temperatures. Particles there move fast enough to escape the Sun's gravity and travel into space. As the plasma moves outward, it carries the Sun's magnetic field with it. The Sun rotates, so the magnetic field becomes stretched into a large spiral across the solar system. Planets move through this changing flow. The solar wind is not perfectly steady. Its speed, density, temperature, and magnetic direction vary. Fast streams can catch slower streams and create compressed regions. Sudden eruptions from the Sun can send large clouds of plasma into space. When one of these disturbances reaches Earth, it pushes against the planet's magnetic environment. The side facing the Sun becomes compressed, while the opposite side stretches far behind the planet. Energy can enter the system through magnetic interactions and changing currents. Particles may be accelerated and guided toward the upper atmosphere. There they collide with oxygen and nitrogen, producing auroras. The light may appear as quiet arcs, moving curtains, rays, patches, or rapidly changing bands. The shape is controlled by magnetic fields and the flow of charged particles. The color depends on the atmospheric particles involved, their altitude, and the energy delivered during collisions. Green is common because of a particular emission from oxygen. Red may appear higher in the atmosphere where collisions are less frequent. Blue and violet light can come from nitrogen. The result is not a simple glow from hot air. It is a visible map of energy entering Earth's atmosphere along magnetic routes. Auroras can be beautiful, but the solar disturbances that produce them may also affect technology. Changing magnetic fields can induce currents in long conductors. Satellites may experience increased radiation and atmospheric drag. Navigation and radio communication can become less reliable. Electrical systems on the ground may be disturbed. This collection of effects is known as space weather. Unlike weather in the lower atmosphere, it is driven mainly by the Sun, plasma, and magnetic fields. Forecasting it requires observations of the Sun, measurements from spacecraft, and models of how charged particles move through space. The Sun itself is a vast sphere of plasma held together by gravity. Its center is hot and dense enough for nuclear fusion. Light atomic nuclei combine and release energy. That energy moves outward through the Sun before eventually escaping as light and heat. The Sun is not burning in the chemical sense. Ordinary fire requires chemical reactions involving atoms and molecules. Inside the Sun, matter is too hot for normal molecules to survive. Electrons are separated from nuclei, and the material exists as plasma. The energy source comes from changes within atomic nuclei rather than chemical bonds. Gravity presses the sun inward, while pressure from the hot interior pushes outward. The balance between these effects allows the sun to remain stable for long periods. If gravity suddenly became stronger without another change, the sun would contract. If internal pressure became too strong, it would expand. Stellar stability depends on these competing processes. The plasma in the sun is not still. Energy moves through it. Hot material rises in some regions while cooler material sinks in others. The surface has a grainy appearance because of this motion. Each bright region marks rising hot plasma, and darker edges contain material moving downward. The sun also rotates, but not like a solid ball. Different latitudes rotate at different rates because the sun is plasma. This uneven rotation helps stretch, twist, and strengthen magnetic fields inside the sun. Over time, magnetic energy builds and produces active regions. Sunspots are darker areas on the visible surface. They're not cold in ordinary terms, but they are cooler than the surrounding plasma. Strong magnetic fields interfere with the normal transport of heat from below, so less energy reaches the surface in those locations. Sunspots often appear in groups with complex magnetic structures. Above them, plasma may follow curved magnetic paths, forming bright loops. These loops can extend far above the visible surface. They are not solid arches. They are regions of hot plasma guided by magnetic fields. Sometimes the magnetic arrangement changes suddenly and releases stored energy. A solar flare can heat plasma, accelerate particles, and produce intense radiation. The event may last from minutes to hours depending on its size and structure. The released energy can affect the sun's atmosphere and the space around it. A larger eruption may throw a cloud of plasma and magnetic field away from the sun. If the cloud travels toward Earth, it may arrive after a period of time and disturb the planet's magnetic environment. Not every eruption is directed toward us, and not everyone produces a major effect. Direction, speed, magnetic orientation, and density all matter. The sun is an ordinary star in many respects, but stars exist across a wide range of sizes, temperatures, colours, and lifetimes. All normal stars spend much of their lives supported by energy released through fusion in hot plasma. Their properties depend mainly on mass and composition. A star with more mass has stronger gravity pressing inward. Its core becomes hotter and denser, allowing fusion to proceed more rapidly. Such stars can shine far more brightly than the sun, but they use their fuel quickly and may live for a much shorter time. Smaller stars consume fuel more slowly. Some can remain active for periods far longer than the present age of the universe. Their surfaces may be cooler and redder, but they are still made largely of plasma. A star's colour gives information about its surface temperature. Cooler stars often appear red or orange. Hotter stars may appear white or blue. This colour is not the same kind of narrow emission seen in a neon sign. A dense stellar surface produces a broad range of light, shaped by temperature and modified by absorption and emission from the surrounding plasma. Dark and bright lines in starlight reveal which elements are present. The same atomic processes studied in laboratory plasma appear in light from distant stars. Hydrogen, helium, calcium, sodium, iron, and many other elements leave recognizable patterns. The strength of these patterns depends not only on how much of an element exists, but also on temperature and ionization. An element may be present but fail to produce a particular line because its electrons are in different states. Astronomers therefore compare many features rather than relying on a single colour. Stars manufacture and distribute many of the elements found in planets and living things. Fusion inside stars builds heavier nuclei from lighter ones. Some elements are created during the later stages of stellar life. Others form during violent explosions or collisions involving dead stars. When a massive star reaches the end of its life, its core may collapse. The outer layers can be thrown into space in a supernova explosion. The event heats and accelerates plasma, sends shock waves through surrounding material, and creates or disperses heavy elements. A supernova remnant may continue glowing for thousands of years. The expanding plasma collides with gas around it, producing strong shocks. Electrons and ions are heated and accelerated. Magnetic fields are compressed and disturbed. The remnant can emit radio waves, visible light, and high-energy radiation. Some stellar cores remain behind as neutron stars. These objects are extremely dense and often possess strong magnetic fields. Plasma around them can be accelerated along magnetic paths. If beams of radiation sweep past Earth as the star rotates, we observe regular pulses. Other collapsed stars become black holes. A black hole itself does not emit ordinary light from within its boundary, but plasma falling toward it can become extremely hot. The material forms a rotating disk, collides, heats, and releases intense radiation before crossing the point from which light cannot return. Some systems produce narrow jets of plasma, moving away from the central region at very high speed. These jets may extend far beyond the surrounding star system or galaxy. Magnetic fields are thought to play a major role in guiding and accelerating the plasma. The largest jets are associated with active galaxies, where enormous black holes draw in surrounding matter. The plasma near the center can release more energy than all the stars in the galaxy combined. Some jets travel across distances measured in thousands or millions of light years. This does not mean the entire jet is packed with dense matter. It may be extremely thin by Earth standards. Its power comes from high particle energies, strong fields, great speed, and enormous scale. Between stars, space is not empty. It contains gas, dust, radiation, magnetic fields, and plasma. Some regions are cold and mostly neutral. Others are heated and ionized by nearby stars, explosions, or shocks. The material between stars is known as the interstellar medium. Hot young stars release ultraviolet radiation that ionizes the gas around them. These regions may glow red from hydrogen and show other colors from oxygen, nitrogen, and sulfur. Dense clouds can also hide newly forming stars from visible light, while other wavelengths pass through the dust and reveal the activity within. Stars form when regions of gas and dust become dense enough for gravity to pull them inward. As a cloud collapses, it heats and fragments. A young star develops at the center of a rotating system. Jets of plasma may be launched along the direction of its magnetic field. The young star eventually becomes hot enough for sustained fusion. Radiation and stellar winds push away some of the remaining material. Planets may form from the disk around it. Plasma therefore participates in both the birth of stars and the changing environment around young planetary systems. On even larger scales, hot plasma exists between galaxies in groups and clusters. Much of the ordinary matter in a cluster may not be inside the galaxies at all. It can occupy the space between them as extremely hot, thin plasma. This plasma emits high-energy radiation because electrons are deflected by ions. Its temperature can reach levels far beyond the surface of the Sun. Yet a person placed in such an environment would not experience heat in the same way as standing near a furnace, because the particles are spread so thinly. The few collisions that occurred would still be dangerous, especially because of the particle energies and radiation, but density changes how heat is transferred. Magnetic fields thread these large plasma regions as well. They are far weaker than fields produced by many laboratory magnets, but they act across enormous distances and over long periods. They influence particle motion, energy transport, and the shape of radio-emitting structures. Plasma may therefore be the most common, visible form of ordinary matter in the universe. The word visible is important because most of the total matter in the universe appears to be something else, known as dark matter. Dark matter does not glow like plasma, and is detected mainly through its gravitational effects. Among the ordinary matter made from atoms, however, plasma dominates much of what astronomers observe. This fact can seem strange because human life depends on cool solids, liquids, and neutral gases. We live in a small region where matter has settled into conditions suitable for rocks, oceans, atmospheres, and biology. Beyond this local environment, stars and thin ionized gas account for an enormous share of the familiar matter that produces light. Even empty-looking space contains charged particles. The number may be very low, but those particles can still carry currents, support waves, and respond to magnetic fields. Plasma does not stop being plasma merely because it is thin. Low density can actually allow some plasma effects to extend farther. Particles collide less often, so they can travel long distances while following electric and magnetic forces. Waves may move across huge regions. Disturbances can spread from the sun to planets. Shocks can travel through space without behaving like sound waves in ordinary air. A shock in plasma is a sudden change in density, temperature, particle speed, and magnetic field. It can form when a fast plasma flow catches a slower one or strikes an obstacle. Particles crossing the shock may be heated or accelerated. Earth creates a large shock in the solar wind because the plasma flow encounters the planet's magnetic environment. The solar wind slows and is redirected around the magnetic field. Similar shocks appear around other planets, stars, supernova remnants, and moving plasma clouds. These shocks help accelerate particles to very high energies. Some charged particles reaching Earth come from the Sun. Others come from sources far beyond the solar system. They travel through space and collide with Earth's atmosphere, creating showers of secondary particles. The universe is therefore filled with plasma motion at every scale. Electrons spiral around magnetic fields. Ions cross shocks. Currents shape glowing loops. Stars release winds. Explosions heat clouds. Galaxies launch jets. Clusters hold vast reservoirs of thin, hot plasma. The range of scales is impressive, but the same principles keep returning. Energy ionizes matter. Charged particles move differently from neutral ones. Electric fields accelerate them. Magnetic fields guide and bend their paths. Their motion creates currents, and those currents create new magnetic fields. This repeated interaction is why plasma develops structure. Without fields, a thin cloud might simply spread. With fields, it can form loops, filaments, sheets, waves, and jets. The plasma changes the field, and the field changes the plasma. That relationship becomes especially important when scientists try to control plasma on Earth. Nature has gravity strong enough to hold a star together, and space large enough to contain enormous eruptions. A laboratory has walls, instruments, and a limited power supply. Researchers cannot rely on stellar gravity, and they cannot allow a fusion plasma to drift across millions of kilometers. They need another method of confinement. Since charged particles respond to magnetic fields, magnets provide the most promising tool. By arranging fields into carefully designed shapes, physicists can guide electrons and ions away from material walls and keep hot plasma circulating inside a controlled region. The idea appears straightforward when described in a sentence. In practice, the particles drift, collide, form waves, build currents, and create instabilities. The magnetic field must not only guide the plasma, it must respond to a system that is constantly changing and producing fields of its own. To see why confinement is possible, and why it remains so difficult, we need to look more closely at the way magnetic fields act as invisible tracks, mirrors, cages, and sometimes imperfect doors. A magnetic field cannot be seen directly, but its effect on plasma is immediate. A charged particle moving through a magnetic field is pushed sideways. The field does not normally pull the particle forward or slow it down. Instead, it changes the direction of motion. The particle begins curving around the field, and if it also has some motion along the field, its path becomes a spiral. Electrons and ions spiral in opposite directions because they carry opposite charges. Electrons turn much more quickly because they are lighter. Ions follow wider paths and respond more slowly. Even when both groups occupy the same plasma, they can behave very differently over short times and small distances. This spiraling motion is the basic reason magnetic confinement is possible. If a charged particle tries to move directly across a magnetic field, its path is bent. It may circle around one region rather than travelling freely toward a wall. Along the direction of the field, however, the particle can move much more easily. A magnetic field therefore guides plasma rather than simply stopping it. A straight magnetic field would not make a complete container. Particles could spiral around it and then escape from either end. To confine plasma for longer, the field must be shaped so that there is no easy path out. One option is to make the field stronger near the ends of a chamber. As particles move toward a stronger region, some are reflected back. This arrangement is called a magnetic mirror. The name is useful, although there is no polished surface and no ordinary reflection. A particle spirals along the field while the field gradually becomes stronger. Its motion changes, and under suitable conditions it turns around before reaching the end. The particle then travels back toward the weaker field in the centre. Not every particle is reflected. Some approach the stronger field at an angle that allows them to escape. A mirror machine can therefore lose particles through its ends. Researchers can improve the design, add more magnetic structures, and control the particle population. But the basic opening remains difficult to close completely. Another approach removes the ends by bending the magnetic field into a ring. If the field lines form closed paths, particles can travel around the ring instead of escaping from a straight tube. This is the idea behind the tokamak, one of the best-known designs for magnetic fusion confinement. A tokamak has a chamber shaped rather like a ring. The plasma circulates inside this chamber, while strong magnetic fields guide the charged particles. Large coils around the machine create part of the field. An electric current driven through the plasma creates another part. Together, these fields form twisted paths that wrap around the ring. The twisting is important. A simple circular field would not hold particles evenly. The field would be stronger on the inner side of the ring and weaker on the outer side. Electrons and ions would drift in ways that gradually separate charge and move plasma toward the walls. By adding another magnetic direction, the field lines become helical, and particles travel around both the short and long directions of the chamber. This helps balance some of the drifts. The tokamak does not hold plasma like a sealed bottle holds water. The plasma does not rest against a solid boundary. It's kept away from most surfaces by magnetic forces, while particles continue moving at great speed. The magnetic arrangement guides their average motion and reduces the rate at which heat and particles escape. Fusion plasma must be extremely hot because positively charged atomic nuclei repel one another. To fuse, they need enough motion to approach very closely. At ordinary temperatures, that happens far too rarely. Heating the fuel gives the nuclei more energy and increases the chance of fusion collisions. At such temperatures, no ordinary material could touch the plasma and remain undamaged. A metal container would melt, vaporize, and add impurities to the fuel. Magnetic confinement is therefore not an optional convenience. It is the only practical way to keep a hot fusion plasma away from solid walls for a useful period. The most common fusion fuel in many experiments uses two forms of hydrogen. Their atoms are heated until the electrons separate, leaving a plasma of free electrons and positive nuclei. If two suitable nuclei fuse, they form new particles and release energy. Some of that energy can heat the plasma, helping future reactions continue. Reaching a high temperature is only part of the challenge. The plasma must also be dense enough and remain confined long enough. A very hot plasma that immediately escapes will not produce much useful fusion. A well-confined plasma that is too cool will not fuse at a sufficient rate. Success requires a workable combination of temperature and density and confinement time. Heating a plasma inside a tokamak can be done in several ways. The electric current flowing through the plasma produces heat because particles collide and resist the current. This works well at lower temperatures, but plasma resistance decreases as the plasma becomes hotter, so additional methods are needed. One method sends fast neutral particles into the plasma. Neutral particles are not deflected by the magnetic field, so they can enter the confined region. Once inside, collisions remove their electrons or transfer energy to the existing particles. The injected particles become part of the plasma and raise its temperature. Another method uses electromagnetic waves. The waves are chosen to interact strongly with electrons or ions moving in the magnetic field. When the frequency and particle motion match in the right way, energy is transferred efficiently. It resembles pushing a swing at the right moment, although the actual process involves enormous numbers of particles and carefully controlled fields. As heating continues, the plasma becomes more difficult to control. Higher temperature means faster particles. Fast particles explore imperfections in the magnetic field more quickly. They can drive waves, create pressure changes, and feed instabilities. The very conditions needed for fusion also strengthen many of the processes that allow energy to escape. Plasma pressure pushes outward. Magnetic fields provide an inward controlling effect, but the balance is delicate. If the plasma pressure becomes too large for the available magnetic field, the plasma can distort the field and move away from its intended position. A tokamak plasma also carries a strong electric current. That current helps create the confining field, but it stores energy and can become unstable. The plasma may develop a large-scale shift, twist, or break in its current pattern. In a severe event, the current can fall rapidly. This is known as a disruption. A disruption can release thermal and magnetic energy in a short period. Heat may strike parts of the chamber. Strong forces may act on the machine. Fast electrons can sometimes form a concentrated beam. Modern tokamaks use monitoring systems and rapid control methods to avoid disruptions when possible and reduce their effects when avoidance fails. The machine constantly measures the plasma. Sensors observe its position, shape, temperature, density, radiation, magnetic activity, and impurities. Computers process this information and adjust magnetic coils, heating power, fuel supply, and other controls. Confinement is an active process, not a magnetic arrangement that can simply be switched on and ignored. Even when there is no major instability, smaller turbulence can carry heat outward. Plasma turbulence includes irregular motion in density, electric potential, pressure, and magnetic field. Tiny swirling structures form and change. They transport particles across magnetic surfaces more quickly than simple collisions would predict. This is one of the main reasons confinement is difficult. A basic picture of particles spiraling neatly around field lines suggests that heat should remain trapped very well. Real plasma contains waves and fluctuations that disturb those paths. Energy leaks outward through a complicated collection of small motions. Researchers try to reduce this turbulence by shaping the magnetic field and controlling the plasma profile. The way density and temperature change from the center to the edge can affect stability. Rotation can also influence turbulence. In some conditions, the plasma suddenly enters a state with improved confinement, as though part of the outward transport has been reduced. This improved state is useful, but it may create new edge behavior. Pressure near the boundary can build until the plasma releases bursts of particles and heat. These events can strike the chamber wall repeatedly. Scientists study methods to make the bursts smaller, spread their energy, or replace them with gentler continuous losses. The edge of the plasma has a difficult job. The center must remain hot, but particles and energy eventually have to leave in a controlled way. Fusion reactions can produce unwanted particles that must be removed. Impurities entering from the wall must be limited. The machine needs a region where exhaust can be directed without allowing the core to cool too much. Tokamaks use a structure called a diverter for this purpose. Magnetic fields guide the outer plasma towards specially designed surfaces at the bottom or another part of the chamber. These surfaces receive much of the escaping heat and particles. They are built from materials chosen to survive intense conditions, although their lifetime remains a major engineering concern. The diverter is sometimes compared with the exhaust system of an engine. That comparison is useful as long as we remember that the exhaust is a stream of extremely hot charged particles guided by magnetic fields. The heat may be concentrated into a relatively small area. Spreading and cooling that flow without contaminating the main plasma is a central problem for future fusion power plants. Materials near the plasma face several types of damage. Heat can melt or erode surfaces. Fast particles can knock atoms out of the material. Neutrons produced by fusion can penetrate deeply and change the structure of components. Atoms released from the wall may enter the plasma and radiate energy away. No material is perfect. Some tolerate high heat but produce troublesome impurities. Others retain hydrogen fuel or become brittle under radiation. Engineers must balance thermal performance, mechanical strength, chemical behavior, cost, maintenance, and safety. The magnetic coils have their own demands. Strong confinement requires powerful fields. Many modern designs use superconducting magnets, which can carry large currents with very little electrical resistance. To remain superconducting, the coils must be kept extremely cold. This creates one of the widest temperature differences found in engineering. The plasma may be hotter than the center of the sun, while the nearby magnet system operates close to the lowest temperatures that can be produced. Layers of vacuum, insulation, shielding, and structural material keep these environments separated. The phrase hotter than the sun can sound alarming, but temperature alone does not describe total heat. Fusion plasma is very thin. It contains far fewer particles in a given volume than ordinary air. A small amount touching a wall would cool quickly, although repeated or concentrated contact could still cause serious damage. The challenge comes from maintaining the plasma continuously and handling the large total power of a working reactor. A second major magnetic confinement design is the stellarator. Like a tokamak, it uses a ring-shaped chamber and twisted magnetic fields. The difference is that much of the twist is created by external coils rather than a large current through the plasma. This can reduce problems connected with plasma current and may support steady operation more naturally. A power plant would ideally run for long periods rather than in short pulses. The stellarator offers advantages for that goal. Its coils are much more complicated. Instead of simple circular shapes, they may bend and twist around the chamber in carefully calculated forms. Designing and manufacturing them requires high precision. The geometry can look as though the magnets were assembled after a lengthy disagreement, but every curve serves a purpose. Early stellarators struggled to confine plasma as effectively as tokamaks. Improvements in computer modelling allowed researchers to design shapes that reduce particle losses. Modern stellarators have achieved much better performance and remain an important route toward fusion energy. Magnetic confinement is not the only method. In inertial confinement, a small fuel target is compressed and heated very rapidly, often using powerful laser beams. The fuel does not remain confined for long. Instead, its own inertia holds it together briefly while fusion reactions occur. The outer layer of the target is heated and blown outward. That outward motion drives the inner fuel inward, producing extreme compression. If the process is sufficiently even and powerful, the center becomes hot enough for fusion. The event takes place over a very short time. This method does not use a magnetic cage in the same way as a tokamak. However, plasma physics is still central. The laser creates plasma on the target surface. Energy must move through that plasma correctly. Instabilities can make the compression uneven. Small imperfections may grow and prevent the fuel from reaching the required conditions. Some concepts combine magnetic and inertial methods. They use magnetic fields to reduce heat loss while compressing the plasma. Others create compact plasma structures that are accelerated, merged, or squeezed. Fusion research includes many designs because no approach has solved every physical and engineering problem. Magnetic confinement is also used outside fusion. Devices can trap low-temperature plasma for experiments, material processing, and particle research. Magnetic fields guide plasma in electric propulsion systems for spacecraft. They help control arcs and shape beams of charged particles. Natural systems use magnetic confinement without human machinery. Earth's magnetic field traps energetic particles in radiation belts. The Sun's field holds plasma in loops above its surface. Some stars possess magnetic fields far stronger than the Sun's, producing intense activity and directing plasma over great distances. Natural confinement is rarely permanent. Solar loops can twist and erupt. Trapped particles can escape or enter the atmosphere. Magnetic fields change as currents move. The same instability seen in a laboratory appears on scales larger than planets. Magnetic reconnection is especially important when confinement breaks or rearranges. Magnetic energy stored in one configuration is rapidly converted into heat and particle motion. In the Sun, this process contributes to flares and eruptions. In Earth's magnetic environment, it releases energy that helps drive auroras. Inside fusion experiments, reconnection can alter the plasma current and contribute to sudden changes. Researchers study it both to prevent damaging events and to understand a general process found throughout the universe. The idea of a magnetic cage should therefore be treated carefully. A cage made from metal bars has a fixed structure. A magnetic cage is produced by currents, and the plasma inside can change those currents and fields. The boundary is flexible. It can ripple, shift, and reconnect. Confinement improves when particle paths remain organized and turbulence stays limited. It worsens when drifts, collisions, waves, and instabilities carry particles across the field. No single magnet solves the problem. The entire system must be shaped, heated, measured, and controlled as one connected machine. This is why fusion progress can appear slow from the outside. Scientists already know how to create fusion reactions. They have done so in many experiments. The harder goal is to produce a stable system that releases useful energy reliably, protects its materials, replaces its fuel, removes waste heat, and operates at a cost that makes sense. A successful reactor would need more than a hot plasma. It would need magnets, power supplies, cooling systems, fuel handling, shielding, turbines or another energy conversion system, maintenance equipment, and a control system able to respond quickly to plasma changes. Each part influences the others. Stronger magnets may improve confinement but increase cost and structural stress. A smaller machine may be easier to build but place more heat on a smaller surface. A material that survives the diverter may introduce impurities. A method that stabilizes the plasma may consume additional power. The art of containment is therefore the art of compromise. Physicists search for plasma conditions that remain stable. Engineers design machines that can survive those conditions. Computer systems adjust the experiment in real time. Material scientists develop surfaces that tolerate heat and radiation. Every improvement opens another set of questions. The work has also produced technology beyond fusion. Powerful superconducting magnets, plasma control methods, vacuum systems, heating equipment, and advanced materials have applications in research and industry. Understanding confinement helps with spacecraft propulsion, semiconductor manufacturing, medical devices, and the study of space plasma. Once plasma can be created and guided, it becomes a practical tool rather than only a subject of observation. It can cut metal, deposit coatings, clean surfaces, produce light, sterilize equipment, and push spacecraft through space. The same charged particles that make confinement difficult can be used precisely because electric and magnetic fields allow their energy and direction to be controlled. Once plasma can be created and guided, it becomes useful in places that seem far removed from stars and lightning. It appears in shop signs, factory equipment, computer chip production, medical research, spacecraft engines, and fusion laboratories. In some applications, the plasma is extremely hot. In others, The surrounding gas remains cool enough to treat plastic, fabric, food packaging, or living tissue. The same state of matter can cut through steel in one machine and clean a delicate surface in another. One of the most familiar examples is the neon sign. A glass tube is filled with gas at low pressure, and electrodes are placed at the ends. When a high enough electrical voltage is applied, free electrons accelerate through the gas. They collide with atoms, creating more ions and electrons. The gas becomes plasma, and some of its atoms are excited into higher energy states. As those atoms return to lower energy states, they release light. Genuine neon produces a strong reddish-orange glow. Many signs commonly called neon signs actually contain other gases or use coloured glass and fluorescent coatings. Argon can help produce blue and violet shades. Helium may produce pinkish light. Different gas mixtures allow sign makers to create a wide range of colours. The tube can be bent into letters, pictures, and decorative shapes because the plasma follows the path inside the glass. It does not need to know whether it is illuminating a restaurant name, a dancing palm tree, or an enthusiastic arrow pointing toward a shop that closed 3 years ago. It only responds to the electric field and the gas around it. The pressure inside the tube is important. At normal atmospheric pressure, electrons collide with particles so frequently that it can be difficult for them to gain enough energy between collisions. At lower pressure, they can accelerate over longer distances. This makes it easier to excite and ionize the gas while using a manageable amount of electrical power. Fluorescent lamps use a similar discharge, but the main light produced inside the plasma is ultraviolet radiation rather than visible light. Mercury atoms in the low-pressure gas absorb energy from collisions with electrons and release ultraviolet radiation. A coating on the inside of the tube absorbs that radiation and emits visible light. The colour of the lamp depends mainly on the materials in the coating. Different combinations can produce warm white, cool white, or other shades. The plasma provides the energy, while the coating changes that energy into a form useful for lighting a room. Compact fluorescent lamps work through the same basic process in a folded or curved tube. They require electronic components to start and control the discharge. The visible light may look steady, although the electrical conditions inside the lamp are continually changing. Plasma lighting has largely been replaced in many homes by light-emitting diodes, but gas discharge lamps remain important in signs, street lighting, specialized equipment, and scientific instruments. Their history also shows how quickly plasma moved from an unusual laboratory effect into everyday technology. A plasma globe offers a more decorative example. The glass sphere contains gas at low pressure, and a high-voltage electrode sits near the center. Electrical discharges form glowing filaments that reach toward the outer glass. When a hand touches the globe, the electric conditions change. The body provides a path that affects the field, so several filaments may gather near the point of contact. The plasma is not attracted because it has recognized a friendly visitor. Its movement is changing in response to the electric environment. The glass keeps the user separated from the discharge, but a plasma globe is still an electrical device rather than a toy containing miniature lightning with no rules. It can interfere with nearby electronics, and should be used according to its instructions. Plasma becomes far more energetic in industrial cutting equipment. A plasma cutter forces gas through a narrow opening while an electric arc ionizes it. The result is a fast jet of hot plasma that can melt metal. The flowing gas also blows molten material away from the cut. The process is useful because the energy is concentrated into a small area. Steel, aluminium, copper, and other electrically conducting materials can be cut quickly and accurately. The machine can create long, straight cuts, curves, and complex shapes under computer control. The plasma jet reaches very high temperatures, but speed and concentration are just as important as temperature. It transfers energy rapidly to the workpiece. A handheld plasma cutter can slice through metal that would resist ordinary mechanical tools, which is impressive, and also a good reason not to test it on anything described as probably unimportant. Plasma arc welding uses related physics. An electric arc creates a controlled stream of plasma that heats and melts the materials being joined. The process can provide a stable, focused arc and precise control over heat delivery. Different welding methods use plasma in different ways. Some form an arc between an electrode and the workpiece. Others maintain an arc inside the torch before transferring energy outward. Shielding gas protects the hot region from unwanted reactions with the surrounding air. Electric arcs are also used in furnaces for melting metals and processing materials. Large currents pass through electrodes and create extremely hot plasma. The energy can melt scrap steel, produce specialized alloys, and support chemical reactions that would be difficult at lower temperatures. These thermal plasmas place much of their energy into the heavy particles as well as the electrons. The entire gas becomes very hot. They are suited to cutting, melting, spraying and destroying material, but not to treating surfaces that need to remain cool. Cold plasma works differently. Its electrons may be energetic enough to cause ionization and chemical reactions, while the ions and neutral particles remain much cooler. The average gas temperature can stay near room temperature or rise only moderately. This separation of particle energies allows cold plasma to act on surfaces without delivering the same level of heat as a flame or arc. Energetic electrons collide with gas molecules and create reactive atoms, ions, and short-lived chemical compounds. Ultraviolet radiation may also be produced. These reactive particles can break apart contamination, damage microorganisms, and change the chemical structure of a surface. Since the treatment can occur at relatively low temperatures, it can be used on plastics, textiles, electronic components, and biological materials. Manufacturers use plasma cleaning before applying paint, glue, coatings, or printed patterns. A surface may look clean to the eye while still carrying thin layers of oil, dust, or chemical residue. Plasma can remove some of this contamination and make the surface easier to bond. It can also change how a surface interacts with water. Some materials naturally repel liquids. Plasma treatment can add or expose chemical groups that make the surface more attractive to water, ink, or adhesive. The bulk material remains mostly unchanged because the effect is concentrated near the surface. A plastic component may therefore become easier to paint without being heated enough to bend. A fabric may accept dye more evenly. A medical device may receive a coating that bonds more securely. The treatment can be adjusted by changing the gas, pressure, power, and exposure time. Plasma deposition uses reactive particles to build thin layers rather than remove them. Gas molecules enter a chamber and are broken apart by the plasma. Their fragments react at a surface and form a coating. These coatings may protect against wear, corrosion, moisture, or chemical attack. They can change electrical properties, optical behavior, or friction. Some are only a small fraction of the thickness of a human hair, yet they can significantly change how a component performs. The electronics industry depends heavily on plasma processing. Modern computer chips contain extremely small patterns of conducting, insulating, and semiconducting materials. Producing those patterns requires precise control at scales far smaller than anything visible to the unaided eye. One important process is plasma etching. A patterned protective layer is placed on a material surface. Reactive particles from the plasma remove exposed regions while leaving protected areas behind. The result is a set of tiny channels, holes, or structures. The plasma must be carefully controlled. It needs enough energy to remove material, but not so much that it damages the layers below. The particles may also need to arrive mostly from one direction, so that the etched features have straight sides rather than spreading sideways. Electric fields inside the processing chamber can guide ions toward the surface. Since ions are charged, their direction and energy can be adjusted. Reactive neutral particles contribute chemical effects, while ions provide controlled physical impact. The combination allows engineers to create features with precise shapes. Without plasma etching, many modern processors, memory devices, sensors, and communication chips would not be possible. Plasma is also used to deposit the thin films needed in those devices. Insulating layers, conducting layers, and protective coatings can be formed from gases activated by plasma. Lower processing temperatures may be used than would be required with ordinary chemical reactions. This is valuable because a computer chip passes through many manufacturing stages. A high-temperature step introduced too late could damage structures created earlier. Plasma provides a way to drive useful reactions without heating the entire component to the same extreme temperature. Flat panel displays, solar cells, optical coatings, and advanced batteries also use plasma-based manufacturing. The finished products may contain no plasma during normal operation. Plasma serves as a tool during production, shaping materials and preparing surfaces. Medical applications use many of the same low-temperature effects. Cold plasma can produce reactive oxygen and nitrogen compounds that damage bacteria, fungi, and some viruses. It may also release ultraviolet radiation and charged particles. This makes plasma useful for sterilizing certain instruments and surfaces. Traditional sterilization methods may require high temperatures, strong chemicals, or long treatment times. Plasma can offer another option for materials that would be damaged by heat. A plasma sterilization system must be designed carefully. The treatment needs to reach the relevant surfaces and produce enough reactive particles to reduce microorganisms. At the same time, it must avoid damaging the instrument or leaving harmful residues. Complex shapes can make this difficult. A smooth exposed surface is easier to treat than a long narrow channel inside a medical device. Engineers study how plasma and reactive gases move through these spaces and how quickly their effects weaken. Researchers are also examining direct plasma treatment of wounds and skin. Low-temperature plasma can be produced in a small jet or discharge and applied for a controlled time. Laboratory studies suggest that it may reduce certain microorganisms and influence biological processes connected with healing. Living tissue is far more complicated than a metal or plastic surface. Reactive particles that damage bacteria can also damage healthy cells if the dose is too high. The electric field, temperature, gas flow, treatment time, and chemical products all need careful control. Medical plasma research therefore involves physicists, engineers, chemists, microbiologists, and doctors. A device that works well on a laboratory sample must still be tested for consistency, safety, and clinical usefulness. Plasma may be helpful, but it does not receive permission to skip the ordinary requirements of medical evidence simply because it glows. Dental researchers have studied plasma for disinfecting surfaces, treating tooth material, and improving bonding. Other groups are exploring its use against certain skin conditions and cancer cells. These areas remain under investigation, and different applications are at different stages of development. Plasma is also being tested in food production. Cold plasma can reduce microorganisms on packaging, equipment, seeds, fruits, vegetables, and other products. Since the gas can remain relatively cool, the treatment may preserve materials that would be changed by strong heating. The shape and texture of food create challenges. A smooth package is easier to treat evenly than a rough leaf or a pile of grains. Organic material can also react with the active particles and reduce their effect. The treatment must be matched to the product. Agricultural research includes plasma treatment of seeds. Exposure may change the seed surface, improve water absorption, or reduce microorganisms. Some experiments report changes in germination and early plant growth, although results depend on species, treatment conditions, and dose. Plasma-activated water is another area of study. A discharge above or within water produces reactive compounds that remain in the liquid for some time. The water can then be used for cleaning, agriculture, or biological experiments. The chemistry is complex because many short-lived and longer-lived compounds can form. Their concentrations depend on the gas, power, treatment duration, temperature, and water composition. Calling it plasma water would be convenient, but the plasma itself may no longer be present after treatment. What remains is water containing chemical products created by the discharge. Environmental applications use plasma to break down pollutants. Energetic electrons can create reactive particles that attack unwanted molecules in gases or liquids. This may help treat exhaust, industrial emissions, contaminated water, and difficult chemical waste. Plasma systems can remove certain nitrogen compounds, sulfur compounds, odors, and organic pollutants. Some designs operate at atmospheric pressure, others use vacuum chambers or liquid discharges. The aim is often to convert harmful molecules into simpler or less dangerous products. This sounds straightforward, but incomplete reactions can produce new compounds that also require attention. A successful treatment must identify what enters the system, what reactions occur, and what leaves it. Plasma can assist in producing useful chemicals as well. Traditional chemical manufacturing often relies on high temperatures, high pressures, catalysts, and large industrial equipment. Plasma supplies energetic electrons that can break stable molecules apart and start reactions under different conditions. Researchers are studying plasma methods for producing hydrogen, ammonia, fuels, and chemical feedstocks. Some processes aim to use renewable electricity and operate in smaller, flexible systems. The challenge is making them efficient enough to compete with established industrial methods. Breaking a molecule is not the same as producing the desired product. The fragments may recombine in several ways. Energy can be lost as heat or radiation. Electrodes and reactor walls may wear down. The chemistry must be guided toward useful outcomes. Plasma torches can also treat solid waste. Extremely high temperatures break complex materials into simpler gases and a melted residue. The residue may cool into a glass-like solid, while the gas can be cleaned or used as a fuel source. This method can handle some materials that are difficult to process conventionally, but it requires substantial energy and careful emission control. Whether it's practical depends on the waste, electricity cost, scale, and treatment goals. Plasma propulsion carries the subject away from factories and back into space. A chemical rocket produces thrust by burning fuel and expelling hot gas at high speed. Plasma engines use electric and magnetic fields to accelerate charged particles. One common design ionizes gas and uses an electric field to accelerate the ions out of the engine. Electrons are released into the exhaust so that the spacecraft does not become strongly charged. The outgoing particles produce thrust in the opposite direction. The thrust may be much weaker than that of a chemical rocket. A plasma engine would not usually lift a spacecraft from Earth's surface. Its advantage is efficiency. It can accelerate particles to very high speeds and use fuel slowly. A small force applied for weeks or months can produce a large change in spacecraft speed. This makes electric propulsion useful for adjusting satellite orbits and sending probes on long journeys. It exchanges strong immediate acceleration for patient, efficient operation. Hall effect thrusters use magnetic and electric fields to control electrons and accelerate ions. They have flown on many spacecraft. Ion engines use related principles with different arrangements of electrodes and fields. Other concepts heat plasma and guide it through magnetic nozzles. A magnetic nozzle directs charged particles outward without requiring them to touch a solid surface in the hottest region. This can reduce damage and allow higher exhaust temperatures. The choice of propellant depends on the engine. Some systems use noble gases because they are easy to store and do not react strongly with spacecraft materials. Other concepts examine more abundant or cheaper alternatives. Plasma propulsion has the same general trade-off seen elsewhere. Stronger electric acceleration can improve exhaust speed but requires more power. A spacecraft far from the sun may have limited solar energy. A nuclear power source can provide more consistent power but adds complexity and mass. Satellites already use plasma-related devices for more than propulsion. Electric discharges can control surface charge, produce beams, and support scientific instruments. Spacecraft also carry sensors that directly measure natural plasma around Earth and other planets. Those measurements help reveal the density, temperature, composition, and flow of charged particles. Instruments detect electric and magnetic fields, plasma waves and energetic particles. A spacecraft can pass through a region that looks empty and discover a changing electrical environment. Back on Earth, the most ambitious plasma project remains controlled fusion energy. Fusion seeks to reproduce the energy-producing process of stars without reproducing the mass, gravity, or dimensions of a star. The fuel must be heated into plasma, confined, and kept stable, long enough for a useful number of nuclei to fuse. Tokamaks and stellarators use magnetic fields to confine the plasma. Laser-driven systems compress tiny fuel targets for extremely short periods. Other designs combine magnetic fields, electrical currents, compression, and rapid heating in different ways. Fusion reactions can release large amounts of energy from a small amount of fuel. The main fuels considered for early reactors are forms of hydrogen. One can be extracted from water, while another may be produced from lithium inside the reactor system. The process does not release carbon dioxide through combustion. It also cannot continue through the same kind of runaway chain reaction associated with some fission accidents. If heating or confinement fails, the plasma cools and fusion stops. That does not make a fusion plant simple or risk-free. High-energy neutrons can damage materials and make some components radioactive. Tritium fuel must be handled carefully. Powerful magnets store large amounts of energy. The machine must manage extreme heat, vacuum, radiation, and mechanical stress. A reactor must also produce its own tritium or obtain a reliable supply. Neutrons from fusion can interact with lithium in a surrounding blanket and create tritium. That blanket would also absorb fusion energy and convert it into heat for electricity generation. The design must collect more tritium than the reactor consumes after accounting for losses, processing time, and reserve needs. Achieving this, while also protecting the magnets and removing heat, is a major engineering task. A power plant must run reliably. A physics experiment can pause, while researchers replace a component or study unexpected behavior. A commercial plant would need predictable maintenance, durable materials, and a high operating schedule. The plasma must be fueled continuously or repeatedly. Helium produced by fusion must be removed. Impurities must be controlled. Heat reaching the diverter must stay within material limits. Magnets and cooling systems must operate efficiently. Producing fusion reactions is therefore only one part of producing fusion electricity. The reactor must generate enough energy to power its own systems and still deliver a useful amount to the grid. Heating, magnets, pumps, fuel processing, cooling, and control equipment all consume power. Progress is measured in several ways. Researchers study plasma temperature, density, confinement time, stability, and energy production. A result that improves one measure may not solve the entire reactor problem. A machine can achieve impressive plasma conditions without yet operating as a complete power station. Experiments have nevertheless made major advances. Plasma can be heated to the required range. Magnetic confinement has improved. Control systems respond faster. Superconducting magnets have become stronger. Materials testing and computer modeling continue to develop. Private companies and public laboratories are exploring several designs. Some aim for larger machines based on established tokamak research. Others use compact high-field devices, stellarators, pulsed systems, or alternative confinement methods. Each approach makes different compromises. A strong magnetic field can allow a smaller plasma, but the magnets and structure face greater demands. A larger machine may confine heat more effectively but cost more and take longer to build. A pulsed system may avoid some steady operation problems while creating repeated mechanical and thermal stress. No design escapes the need to understand plasma behavior. The particles still move, collide, drift, form waves, and generate currents. The plasma still responds to the machine while changing the conditions inside it. This is the connection between a neon sign and a fusion reactor. They differ enormously in temperature, size, pressure, purpose, and complexity. Yet both begin by placing energy into gas and creating free charged particles. Both depend on electric fields, collisions, excitation, and ionization. Both must sustain plasma without allowing it to behave in an unwanted way. In a sign, unwanted behavior might cause flickering, overheating, or failure. In a manufacturing chamber, it might damage a microscopic circuit pattern. In a medical device, it could deliver the wrong dose of reactive particles. In a spacecraft engine, it could reduce thrust or erode a component. In a fusion reactor, it could release heat toward the wall and end the discharge. Control is therefore central to every practical use of plasma. Engineers choose a gas, pressure, power source, chamber shape, and field arrangement. Sensors measure the result. The system is adjusted until the plasma produces the desired effect. There is no single plasma machine because there is no single useful plasma condition. A cutting torch needs concentrated heat. A sterilization device needs reactive chemistry at a low gas temperature. A chip factory needs precise ion direction. A spacecraft engine needs fast exhaust. A fusion reactor needs extreme temperature with limited energy loss. The applications may appear unrelated because the final goals are different. Plasma physics connects them through the behavior of electrons, ions, fields, collisions, and radiation. This also explains why plasma can be both ordinary and difficult to notice. A person may use products made with plasma every day without ever seeing the plasma itself. The computer, phone, solar panel, coated window, medical tool, and manufactured packaging may all have passed through plasma processes. Plasma is not only found in spectacular flashes or giant machines. It works quietly inside sealed chambers on factory floors. It cleans, removes, deposits, excites, accelerates, and transforms material one surface at a time. Its range of uses gives us enough examples to return to the central question with more care. Calling plasma the fourth state of matter is helpful, but it does not fully explain why a weakly glowing gas, a lightning channel, the solar wind, and a fusion fuel belong in the same category. To bring those cases together, we need to decide which properties are essential and which are only common appearances. Calling plasma the fourth state of matter is useful because it places the subject beside solids, liquids, and gases. It gives us a simple starting point. A solid can melt into a liquid. A liquid can become a gas. A gas can gain enough energy for some of its electrons to separate from atoms, producing plasma. That sequence is easy to remember, but it can also make plasma sound like one more item in a tidy list. The real situation is less tidy and much more interesting. Plasma is not defined by one temperature, one color, one density, or one method of creation. It is defined by the presence of free charged particles and by the way those particles behave together. A plasma contains electrons that are no longer bound to individual atoms, positive ions left behind after electrons have been removed, and often neutral atoms or molecules as well. These particles respond to electric and magnetic fields. Their motion creates currents. Those currents create additional fields. A change in one region can influence particles far beyond the location of the original disturbance. That collective response is the part that turns an ionized gas into something more than an ordinary gas with a few loose electrons. A gas can contain a small number of ions without behaving strongly as plasma. Natural radiation, ultraviolet light, and energetic collisions create occasional charged particles in ordinary air all the time. The air around you does not normally form glowing filaments or follow magnetic field lines because the charge population is too small and too quickly neutralized to control the behavior of the whole gas. When the charged particles become numerous enough, energetic enough, or long-lived enough to interact collectively, the gas begins showing plasma behavior. Electric disturbances are screened by the movement of surrounding charges. Currents can flow, waves can travel through changes in charge, density, and fields. Magnetic forces can guide the particles into spirals and organized structures. The system has crossed into a condition where electrical effects matter across more than isolated collisions. This is why a fixed percentage of ionization cannot define every plasma. One plasma may be almost completely ionized, while another contains mostly neutral particles. Both can belong to the same broad state of matter if the charged component has a strong influence on the system. A fluorescent lamp contains a partially ionized gas. The center of a star is far more completely ionized. The temperatures, pressures, and particle densities are different, but both contain mobile charges that behave collectively. It is also why the phrase hot gas is incomplete. Many plasmas are hot because heating is an effective way to ionize matter. Stars, lightning channels, welding arcs, and fusion experiments all involve high temperatures. Cold plasma, however, can be produced when electrons gain much more energy than ions and neutral particles. The electrons cause ionization and chemical reactions, while the bulk gas remains relatively cool. Such plasma can treat plastic, clean surfaces and interact with biological material without delivering the heat of a torch. The word cold does not mean that every particle is moving slowly. It means that the heavy particles remain much cooler than the most energetic electrons, or that the overall gas temperature stays low enough for the intended application. Plasma temperature can be complicated because different particle groups may not share the same energy distribution. Electrons, ions, and neutral particles can each have different average energies. A small population of fast particles may also behave very differently from the majority. This mixture of conditions is one reason plasma physics needs several ways of describing the same system. At a large scale, plasma may behave like a flowing fluid with pressure, density, temperature, and currents. At a smaller scale, individual particle paths become important. Electrons spiral tightly around magnetic fields. Ions follow wider curves. Collisions scatter both groups. Some particles become trapped, while others escape. The correct description depends on the question being asked. When the goal is to understand the shape of a solar eruption, a fluid description may reveal how magnetic fields and plasma move together. When the goal is to understand how an energetic electron damages the wall of a fusion device, the path of that individual particle matters. Neither view replaces the other. Plasma is both a collection of particles and a medium that develops large-scale behavior. This dual nature appears in every example we have considered. A neon sign glows because individual electrons collide with individual atoms, but the discharge can continue only because the charge population and electric field sustain one another. Lightning forms through countless local ionization events, yet the result is a current channel stretching across a large part of the sky. The solar wind contains individual particles moving through space, but it also carries waves, shocks, currents, and magnetic structures across the solar system. The sun shows the full scale of this connection. Fusion reactions occur through interactions between atomic nuclei in the core. The energy produced there moves through a vast sphere of plasma. Convection carries hot material upward and cooler material downward. Currents generate magnetic fields. Those fields produce loops, sunspots, flares, and eruptions. Processes that begin with particles end by shaping structures larger than Earth. Plasma is sometimes described as electrically neutral, which may sound like a contradiction. If it is made from charged particles, how can it be neutral? The answer is that positive and negative charge usually balance over large distances. A plasma may contain an enormous number of electrons and ions, while carrying little total charge overall. The charges remain separate and mobile even when their totals are nearly equal. Small imbalances still occur. Electrons can move away from ions more quickly because they are lighter. A region may become slightly positive or negative. The resulting electric field then pushes particles in a direction that tends to restore balance. Plasma is not neutral because nothing electrical is happening. It is close to neutral because electrical activity continually prevents large charge separation from lasting. This behavior is known as shielding. When an extra charged object is placed in plasma, nearby electrons and ions rearrange around it. Opposite charges gather closer, and similar charges move away. The electric influence of the object becomes weaker beyond a limited region. The plasma does not remove the charge, but it hides much of its effect from distant particles. Shielding is an essential sign of collective behavior. It shows that the plasma can reorganize itself as a group. The distance over which shielding occurs depends on temperature and particle density. In dense, cooler plasma, the response may happen over a short distance. In thin, energetic plasma, the affected region can be larger. Scientists use this and related properties to decide whether a charged gas should be treated as plasma. Another key feature is the ability to support waves. If electrons are displaced slightly from ions, the electric attraction pulls them back. Their momentum carries them past the balanced position, and they oscillate. Other waves involve pressure, magnetic fields, ion motion, or combinations of these effects. Some travel smoothly, others grow unstable, break apart, or transfer energy to particles. An ordinary gas supports sound waves because pressure disturbances move through collisions. Plasma supports sound-like waves and many additional types because its charged particles interact through fields. A disturbance does not always need to wait for one particle to bump into the next. Electric and magnetic forces can connect regions over greater distances. This connection does not make plasma perfectly organized. It often creates the opposite result. Multiple waves can overlap, currents can concentrate into filaments, magnetic fields can twist, density changes can grow, turbulence can move heat and particles across a confined region. Plasma can form detailed structure while remaining difficult to predict. That combination explains why plasma sometimes appears almost alive. Auroral curtains move, solar loops bend, lightning branches, and plasma globes produce wandering filaments. There is no awareness or intention behind these motions. They come from feedback. Particle motion creates fields. Fields alter particle motion. The changed motion creates new fields. A simple disturbance can grow into a moving pattern. The same feedback makes plasma useful. Electric fields can accelerate particles. Magnetic fields can guide them. Gas composition can be chosen to produce specific chemical reactions or colors. Pressure can be adjusted to control collision rates. Power can be delivered continuously, in pulses, or through electromagnetic waves. Engineers can shape plasma for a particular task. A plasma cutter concentrates energy into a fast, hot jet that melts metal. A semiconductor chamber uses ions to remove material from microscopic patterns. A coating system uses reactive fragments to build a thin film. A sterilization device creates particles that damage microorganisms. An ion engine accelerates charged atoms to push a spacecraft. A fusion experiment heats hydrogen fuel and attempts to keep it confined long enough for nuclei to join. These machines do not use the same plasma condition. In fact, a plasma suited to one task might be useless for another. A hot arc would destroy a computer chip. A weak low-temperature discharge would not cut steel. A fusion plasma must minimize impurities, while a lighting tube may depend on a carefully chosen mixture of gases. Plasma is a category of behavior, not a single substance that can be poured from one device into another. It is similar to the word liquid. Water, oil, molten metal, and alcohol are all liquids, but they do not have the same temperature, chemistry, density, or purpose. What they share is a form of physical behavior. Plasma covers an even wider range because electrical and magnetic effects add many new possibilities. The label fourth state of matter should also not be taken to mean there are only 4 states. Physics recognizes many other forms of matter under special conditions. Some occur at extremely low temperatures, others appear under enormous pressure or inside dense astronomical objects. Plasma is called the fourth state, mainly because it is common, important, and a natural extension of the solid, liquid, and gas sequence. Even that sequence is not always followed. Matter does not need to pass through every earlier state before becoming plasma. A strong laser can ionize a solid surface almost immediately. An electric discharge can create plasma in gas without heating the entire gas to an extreme temperature. Intense radiation can ionize the upper atmosphere. Fast particle impacts can create plasma in space or in laboratory materials. Plasma can also interact with solids and liquids at the same time. A discharge may form above a liquid surface. An arc may vaporize metal and add it to the plasma. Dust particles can become charged and float within plasma. These dusty plasmas can form organized structures because the charged grains interact with the surrounding electrons, ions and fields. Dusty plasma appears in industrial chambers and in space. Planetary rings, comet tails and regions around young stars may contain charged dust mixed with plasma. In a laboratory, the grains can arrange themselves into layers and repeating patterns that are large enough to see directly. They provide a useful way to study collective behavior without needing to observe individual electrons. There are also plasmas where the positive and negative particles have equal mass. Ordinary plasma contains light electrons and much heavier positive ions. In a plasma made from electrons and their positively charged counterparts, both groups respond on similar timescales. This changes the types of waves and structures the plasma can support. Such conditions may occur near energetic astronomical objects and can be created in specialized experiments. These examples show that the central idea is broader than ionized air or hot hydrogen. Plasma is any sufficiently collective system of mobile charged particles, although the exact definition is adjusted to the environment being studied. The particles may come from atoms, molecules, antimatter, or charged dust. They may be nearly balanced overall while remaining individually free to move. A useful definition should explain both what plasma contains and what it does. It contains mobile positive and negative charges. It responds collectively to electric and magnetic fields. It can screen charge, carry current, support waves, and form structures. It may also contain neutral particles, emit radiation, and change rapidly when energy is added or removed. This definition leaves room for the great variety seen in nature. Lightning is plasma because the ionized channel carries current and responds to fields. The sun is plasma because its electrons and nuclei move collectively while generating magnetic activity. The ionosphere is plasma because charged particles influence radio waves and respond to solar conditions. A neon sign is plasma because a sustained electrical discharge creates mobile charges and excited atoms. A fusion fuel is plasma because its free electrons and ions must be heated and magnetically confined. It also explains what plasma is not. It is not simply any glowing material. Hot metal can glow without becoming plasma. Chemical reactions can emit light without producing a collective charged gas. It is not simply any gas containing one ion. Ordinary air always contains a few charged particles. It is not always extremely hot. Low-temperature plasma is common in industry and research. It is not a particular chemical element. Almost any material can become plasma if enough energy separates charges under suitable conditions. Plasma is not energy by itself either. People sometimes speak as though plasma were pure energy, especially in fictional settings. Plasma is matter. It contains particles with mass. Those particles may carry large amounts of kinetic, electrical or thermal energy, but the plasma is still a physical material. A lightning channel is ionized air. The sun contains atomic nuclei and electrons. A plasma torch uses a gas such as air, nitrogen, argon, or another chosen material. The idea of pure energy is not needed to make plasma impressive. Ordinary matter already behaves in extraordinary ways when its electrons become free. The ability to conduct current, respond to fields, emit radiation, and organize itself across large distances is enough to explain much of what makes plasma distinctive. The role of magnetic fields deserves special emphasis because it separates many plasmas from neutral gases. A neutral gas may be pushed by gravity, pressure, collisions, and ordinary fluid motion. Plasma experiences all of those effects and also reacts strongly to electromagnetic fields. A weak field acting over enough time can guide particles, shape flows, and store energy. In a fusion machine, strong magnets attempt to keep hot particles away from the walls. In Earth's magnetic environment, the field redirects the solar wind and guides particles toward the poles. In the Sun, magnetic fields emerge from moving plasma and later control loops and eruptions. In galaxies, much weaker fields influence plasma over enormous distances. Magnetic fields can appear to be carried by plasma, but that description has limits. Under many conditions, the plasma and field move together closely. Under other conditions, collisions, electrical resistance, or small-scale particle effects allow the connection to change. Magnetic reconnection can then release stored energy and rearrange the system rapidly. This is another reminder that plasma is not one simple phase with one simple rule. Its behavior changes across scales. Large regions may look smooth, while small regions contain sharp currents. The center of a plasma may be stable, while the edge is turbulent. Electrons may follow the magnetic field closely, while ions respond more slowly. A fluid model may work for one process and fail for another. Scientists do not consider this variety a weakness in the concept. It is the reason plasma physics is a field of its own. The subject links atomic behavior, electricity, magnetism, fluid motion, thermodynamics, radiation, and nuclear processes. It provides a common language for phenomena that would otherwise seem unrelated. A spark from a fingertip, an aurora above the Arctic, a jet from a distant galaxy, and a discharge used to manufacture a microchip can all be studied through the movement of charged particles. Their scales differ so greatly that no single experiment can reproduce them all, yet the same physical ideas continue to apply. That continuity is useful when moving between Earth and space. Laboratory experiments test how plasma waves grow, how reconnection begins, and how turbulence transports energy. Spacecraft then measure similar processes in the solar wind or around planets. Observations of stars and galaxies extend the comparison to much larger and more energetic systems. The exchange works in both directions. Space observations reveal plasma conditions that cannot be created easily on Earth. Laboratory measurements provide detailed control that astronomy cannot. Computer models connect the two, testing whether the same mechanisms explain what is seen. Despite decades of research, plasma continues to present open problems. Scientists are still working to predict turbulence accurately, control fusion instabilities, explain some forms of particle acceleration, and understand how magnetic energy is released across different environments. The basic definition is clear, but the consequences remain rich enough to support entire careers. That does not mean plasma is mysterious in the sense of being unknowable. It means that simple rules can produce complicated results when enormous numbers of charged particles interact. Weather is also difficult to predict, even though air follows known physical laws. Plasma adds long-range electromagnetic forces, rapid changes, and many overlapping scales, making the challenge even greater. The question of what plasma really is can now be answered without relying on a slogan. Plasma is matter in which enough charged particles are free to move that electric and magnetic effects shape the behavior of the material as a whole. It may be hot or relatively cool, dense or thin, bright or invisible, almost fully ionized or only partly ionized. What matters is that the charges act collectively. The phrase fourth state of matter remains a useful introduction, but the collective behavior is the deeper answer. Plasma is not merely gas after more heating. It is gas whose electrical structure has become active. Electrons and ions are no longer locked together inside neutral atoms. They can separate, flow, oscillate, spiral, collide, and build currents. Through those currents, the plasma helps create the fields that guide it. This is why it fills stars, carries solar storms, creates lightning, powers glowing signs, shapes industrial processes, and may one day support practical fusion energy. The same freedom of charge that makes plasma difficult to control also makes it useful. It can transport energy, respond quickly, and be shaped without ordinary physical contact. A person looking at a neon sign sees colour. A welder sees concentrated heat. A chip manufacturer sees a precise tool. A spacecraft engineer sees efficient propulsion. A solar physicist sees magnetic loops and eruptions. A fusion researcher sees fuel that must be kept stable. All are looking at different expressions of the same physical state. When gas wakes up, it does not simply become brighter. Its particles gain new freedom. The electrons begin moving separately from the ions. Electric fields accelerate them. Magnetic fields bend them. Collisions create more charge or return particles to neutrality. Waves carry disturbances. Currents build structure. Light records the transfer of energy. That is plasma in practical terms. It is ordinary matter behaving collectively because its charges are free. After following it from a small discharge to the largest glowing structures in the universe, the word no longer needs to sound exotic. Plasma is uncommon in the quiet conditions of a living room, but it is normal across much of nature. The solids, liquids, and neutral gases around us exist because Earth offers a relatively cool and sheltered environment. Beyond that shelter, matter is often ionized, moving and connected by fields. The next time lightning crosses the sky, an aurora appears in a photograph, or a glowing sign colours a dark street, the visible light will show only part of what is happening. Behind the glow, electrons are leaving atoms, ions are responding, fields are changing, and energy is moving through a collective system. The same process continues in places too distant to see directly. It moves through the sun, the solar wind, the space around planets, the clouds between stars, and the hot material around collapsed objects. Some of that plasma is bright enough to reveal entire galaxies. Some is so thin that it can be detected only through instruments. It remains part of the same physical story. There is no need to remember every technical detail at once. Plasma is charged matter that behaves together. That single idea connects the glow, the heat, the magnetic motion, and the wide range of applications. Everything else develops from it. If this journey has made the fourth state of matter feel more familiar, you may notice plasma more often than before. It is present in the flash above a storm, the coloured tube above a shop, the manufacturing process behind a computer chip, and the sunlight arriving through the window. You can share where you have seen plasma in everyday life, and whether any example surprised you. A like and a subscription also help this channel continue making long, calm explanations of subjects that usually arrive with too much speed and not enough context. Wherever you are listening from, the air around you is probably cool and mostly neutral. High above you, parts of the atmosphere contain free electrons and ions. Farther away, the solar wind moves around Earth. Beyond that, the sun continues holding an enormous mass of plasma through gravity and magnetic fields. Plasma is not fire, not pure energy, and not only hot gas. It is matter containing mobile charges that interact collectively through electric and magnetic fields. Once those charges are free, an ordinary gas begins behaving in an entirely different way, and that is what plasma really is.